We think the laws of physics are eternal rules carved into the fabric of reality itself. Gravity will always pull objects together. Light will always travel at the same speed. Electrons will always orbit atomic nuclei in the same predictable patterns. These seem like the most fundamental truths of existence, as unchanging as mathematical theorems. But what if we're completely wrong? What if the laws of physics are not eternal commandments, but temporary guidelines? What if our entire universe is operating under a cosmic rulebook that could be rewritten at any moment? This isn't science fiction or philosophical speculation. This is a serious hypothesis being discussed by some of the world's most brilliant physicists, including Sean Carroll, Max Tegmark, Leonard Susskind, and Roger Penrose. Think about it this way. We assume that the speed of light, the strength of gravity, and the fundamental forces that hold atoms together have always been the same and will always remain the same. But this assumption is just that, an assumption. We've never actually proven that physical laws must be permanent. We've simply observed them being consistent for the relatively brief period we've been able to study them. The implications are staggering. If the laws of physics are temporary, then everything we know about the universe, from the smallest quantum particles to the largest galaxy clusters, exists within a fragile window of cosmic stability. Outside that window, reality itself might be completely unrecognizable. The universe might literally have an expiration date. This possibility forces us to question everything we think we know about existence. Are we living in a brief moment of cosmic stability between periods of complete chaos? Could the fundamental rules that govern atoms, stars, and galaxies simply stop working one day? The answers might reshape our entire understanding of science, philosophy, and our place in the cosmos. But what exactly do we mean by laws and constants? And how could they possibly change? To understand how the laws of physics might change, we first need to grasp what we mean by fundamental constants. These are the unchanging numbers that appear in every equation, describing how our universe works. They're like the settings on a cosmic control panel that determine everything from how atoms stick together to how fast the universe expands. Let's start with the speed of light, represented by the letter c. This isn't just about how fast light travels through space. The speed of light is woven into the very fabric of space-time itself. It determines how energy and matter relate to each other through Einstein's famous equation E equals mc squared. It sets the ultimate speed limit for any information or influence traveling through the universe. Currently, light travels at about 299,792,458 meters per second in a vacuum. This number appears in countless physics equations. But here's the mind-bending question. What if this number could change? What if tomorrow, light suddenly traveled twice as fast or half as fast? The consequences would be absolutely catastrophic. Atoms would no longer be stable. The nuclear reactions powering stars would either shut down or explode violently. The electromagnetic forces holding molecules together would completely reorganize. Life as we know it would be impossible. Then there's the gravitational constant, known as Big G. This determines how strongly massive objects attract each other. It's why you stick to the ground instead of floating away, why planets orbit stars, and why galaxies hold together instead of flying apart. The gravitational constant is incredibly tiny compared to other forces, which is actually crucial for the universe we inhabit. If gravity were much stronger, stars would burn out in thousands of years instead of billions. If it were much weaker, stars and planets might never form at all. Planck's constant, written as h-bar, governs the quantum world. It determines the scale at which quantum effects become important and sets the fundamental graininess of energy and matter. This constant defines the boundary between the smooth, predictable world we experience and the bizarre, probabilistic realm of quantum mechanics. Change Planck's constant, and you change the very nature of atomic structure and chemical bonding. Perhaps most mysterious is the fine structure constant, represented by the Greek letter alpha. This dimensionless number, approximately equal to 1 divided by 137, determines the strength of electromagnetic interactions. It controls how tightly electrons bind to atomic nuclei, how atoms absorb and emit light, and ultimately how chemistry works. The fine structure constant has puzzled physicists for decades because it appears to be perfectly tuned for complexity to emerge in the universe. The cosmological constant, represented by the Greek letter lambda, is perhaps the most controversial of all. It's related to the mysterious dark energy that's causing the universe's expansion to accelerate. This constant is so incredibly small that it should theoretically be zero, yet observations show it has a tiny but non-zero value. This discrepancy between theory and observation is one of the biggest unsolved problems in physics. Now, here's where things get truly fascinating. For over a century, physicists have assumed these constants are truly constant, unchanging throughout space and time. But what if they're not? What if these fundamental numbers that govern reality have been slowly drifting over cosmic timescales? The first hints that constants might not be constant came from studying light from distant quasars. Quasars are incredibly bright objects powered by supermassive black holes in distant galaxies. When we observe them, we're seeing light that has traveled for billions of years to reach us. This light carries information about the physical conditions when and where it was emitted. In the late 1990s and early 2000s, several research teams began noticing something strange. The spectral lines in quasar light, which depend on the fine structure constant, appear to be slightly different from what we observe in laboratory experiments today. The differences were tiny, only a few parts per million, but they were measurable and consistent across multiple observations. Dr. John Webb at the University of New South Wales led some of the most compelling studies. His team analysed light from distant quasars using the Keck telescopes in Hawaii and found evidence that the fine structure constant was smaller in the past by about 5 parts per million. This might sound insignificant, but it would mean that the fundamental strength of electromagnetic interactions has been slowly increasing over billions of years. Other research groups, including teams led by Dr. Michael Murphy, found similar results. They studied absorption lines created when quasar light passes through intervening gas clouds billions of light years away. These absorption lines act like cosmic fingerprints, revealing the physical constants that were operating when the light was absorbed. Multiple independent studies suggested that the fine structure constant has indeed been changing over cosmic time, but the evidence isn't universally accepted. Other research teams, using different telescopes and analysis methods, have found no evidence for changing constants. Some studies suggest the fine structure constant might be increasing in one direction across the sky, while decreasing in another, implying that physical laws might vary not just in time, but also in space. This would be even more revolutionary than simple time variation. The controversy highlights a crucial point about science at the frontiers of knowledge. We're dealing with incredibly subtle effects that push our instruments and analysis techniques to their absolute limits. The claimed variations in the fine structure constant are so small that they're barely detectable even with our most sophisticated equipment. Yet if real, they would represent one of the most profound discoveries in the history of science. What makes this even more intriguing is that theoretical physics provides several mechanisms by which constants might change. In many theories that attempt to unify the fundamental forces, what we call constants, are actually dynamic fields that can evolve over time. String theory, for example, predicts that the fundamental constants we observe depend on the size and shape of extra dimensions that we can't directly perceive. If these extra dimensions change size over cosmic time, the constants we measure would change as well. Quantum field theory also allows for the possibility that the vacuum of space itself might be unstable. The values of fundamental constants might depend on which of many possible vacuum states the universe happens to occupy. If the universe transitions from one vacuum state to another, the constants would change abruptly. Even more mind-bending is the possibility that the constants might be evolving towards some final, stable configuration. Just as a ball rolling down a hill seeks the lowest point, the fundamental constants might be slowly adjusting themselves toward values that represent the true ground state of reality. We might be living during a transitional period when the universe is still settling into its final form. Consider what this means for our understanding of the cosmos. If the fine structure constant was different in the past, then the early universe operated under subtly different physical laws than today. Stars in the early cosmos would have burned differently. The first galaxies would have formed under slightly altered rules. The chemical elements forged in ancient supernovas would have different properties than the same elements today. This raises profound questions about the history of the universe and the emergence of life. Did life appear when physical constants happened to reach values conducive to biological complexity? Are we living in a special epoch when the constants are temporarily suitable for conscious observers? Or are the constants themselves somehow influenced by the presence of observers in a cosmic feedback loop that challenges our understanding of causality? The implications extend far beyond academic physics. If fundamental constants can change, then the future might be very different from the present. The nuclear reactions that power stars might gradually weaken, leading to a universe that grows cold and dark sooner than expected. Or they might strengthen, causing stars to burn out rapidly in violent explosions. The electromagnetic forces that hold atoms and molecules together might drift to values that make complex chemistry impossible. Even more unsettling is the possibility that constant variation might accelerate. If the fundamental constants are slowly drifting now, what's to prevent that drift from speeding up? Could we witness dramatic changes in physical law within human timescales? The prospect is both terrifying and fascinating, but the most profound implication might be philosophical. The idea of unchanging physical laws has been central to scientific thinking since Newton. It's what allows us to make predictions, design technologies, and understand the cosmos. If the laws themselves are temporary, then science becomes less about discovering eternal truths and more about characterizing the current phase of cosmic evolution. This doesn't make science less valuable, but it does make it more humble. Instead of uncovering the permanent architecture of reality, we might be mapping the temporary rules of a universe in constant flux. Our scientific theories would be snapshots of transient cosmic conditions, rather than timeless descriptions of eternal laws. Yet this possibility also opens up incredible new frontiers for research. If constants can change, then understanding how and why they change becomes one of the most important questions in physics. We might develop new technologies based on manipulating fundamental constants. We might discover that consciousness itself plays a role in determining physical law. We might find that the universe is far stranger and more dynamic than we ever imagined. The search for varying constants continues at observatories around the world. New telescopes with unprecedented sensitivity are being built specifically to test whether fundamental constants have changed over cosmic history. Laboratory experiments are pushing the boundaries of precision to detect any hint of temporal variation in the constants. Theoretical physicists are developing increasingly sophisticated models of how and why constants might evolve. Whether or not fundamental constants actually vary remains an open question. But the mere possibility has already revolutionized how physicists think about the nature of physical law. It has forced us to question our most basic assumptions about the permanence and universality of the rules governing reality. And this is just the beginning. If constants can drift slowly over time, what about the possibility that the laws of physics themselves could change completely? What if the very framework of quantum mechanics, relativity, and thermodynamics that we take for granted could be rewritten by cosmic processes beyond our current understanding? But constants drifting is mild compared to laws themselves changing entirely. The possibility that fundamental constants might drift over time is already mind-bending, but it represents just the tip of the iceberg. What if the very laws of physics themselves could undergo dramatic transformations? What if the basic rules governing reality could be completely rewritten, not gradually over billions of years, but suddenly and without warning? To understand how this might happen, we need to think about physics changes in terms of different levels of severity. Imagine the laws of physics as a complex machine with multiple layers of operation. Changes at different levels would have vastly different consequences for the universe and everything in it. At the mildest level, level A, we have the constant drifting we discussed earlier. The fundamental equations of physics remain the same, but the numbers plugged into those equations slowly change over time. Think of it like adjusting the settings on a cosmic control panel. The machine keeps running, but its output gradually shifts. For example, if the fine structure constant slowly increased, atoms would bind more tightly to their electrons. Chemical reactions would require different amounts of energy. Stars would burn at different rates and emit different colors of light. The universe would still be recognizable, but subtly different. Galaxies would still exist, planets would still orbit stars, and the basic architecture of reality would remain intact. However, the details of how everything operates would be slowly shifting. This level of change might actually be beneficial in some ways. If the cosmological constant were decreasing, the accelerating expansion of the universe might slow down, giving galaxies more time to form complex structures before being torn apart by dark energy. If the gravitational constant were slightly increasing, it might help counteract the expansion and keep cosmic structures bound together more tightly. But level B changes are far more dramatic. At this level, entire fundamental interactions begin to weaken or disappear altogether. Imagine if gravity itself started to fade away. Initially, you might not notice much difference in your daily life. Objects would still fall when dropped, and you'd still feel your normal weight. But over time, as gravity weakened, the consequences would become catastrophic. First, the orbits of planets would begin to decay. Earth would slowly spiral away from the sun, taking us into the cold darkness of interstellar space. But even before that happened, the sun itself would begin to change. The gravitational pressure that keeps the sun's nuclear fires burning would weaken, causing the fusion reactions at its core to slow down. The sun would dim and eventually go out entirely. On larger scales, galaxies would begin to fly apart as the gravitational glue holding them together weakened. Stars would drift away from their galactic homes, wandering alone through an increasingly empty universe. Eventually, even the solar system would disintegrate, with planets drifting away from the sun and moons escaping from their parent worlds. Alternatively, imagine if electromagnetism began to weaken. This would be even more immediately devastating than losing gravity. Electromagnetic forces hold atoms together and allow electrons to orbit atomic nuclei. As this force weakened, atoms would begin to fall apart. Chemical bonds that hold molecules together would break. Your body, which is essentially a complex arrangement of molecules held together by electromagnetic forces, would literally disintegrate. But perhaps most terrifying of all would be level C changes. where the fundamental laws of physics themselves break down completely. This wouldn't be a matter of constants changing or forces weakening. This would be a complete rewriting of the cosmic rulebook. Imagine if quantum mechanics suddenly stopped working. The probabilistic nature of atomic behavior that allows electrons to exist in stable orbits around nuclei would vanish. Atoms would either collapse instantly or explode outward. The uncertainty principle that prevents us from knowing both the position and momentum of particles with perfect precision would disappear, potentially causing reality to behave in completely unpredictable ways. Or consider what would happen if causality itself broke down. In our current universe, causes precede effects. If you drop a ball, it falls because gravity acts on it after you release it. But what if this fundamental ordering of events could be violated? Effects might precede their causes, creating paradoxes and logical contradictions that make the universe fundamentally incoherent. Even more mind-bending would be the breakdown of conservation laws. Energy and matter are currently conserved, meaning they can neither be created nor destroyed, only transformed from one form to another. But what if this rule stopped applying? Matter might spontaneously appear or disappear. Energy might drain away into nothingness or explode into existence from nowhere. The entire foundation of physics would crumble. These level C changes would represent what physicists call phase transitions in the structure of physical law itself. Just as water can suddenly transform from liquid to gas when it reaches its boiling point, the universe might suddenly transform from one set of physical laws to a completely different set. Such transitions have actually happened before in cosmic history. In the first moments after the Big Bang, the universe underwent a series of phase transitions that separated the fundamental forces and established the physical laws we observe today. During the earliest fraction of a second, all four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were unified into a single superforce. As the universe cooled and expanded, this unity was broken through a process called spontaneous symmetry breaking. First, gravity separated from the other forces. Then, the strong nuclear force split off. Finally, electromagnetism and the weak nuclear force, which had been unified as the electroweak force, separated into the distinct interactions we observe today. Each of these transitions fundamentally changed how the universe worked. Before electromagnetism and the weak force separated, particles behaved very differently than they do now. Electrons and neutrinos were essentially the same type of particle. Photons, the particles of light, didn't exist in their current form. The rules governing particle interactions were completely different. These early phase transitions shaped everything about our current universe. The relative strengths of the fundamental forces, the masses of particles, the way matter and energy interact, all of these were determined by how the universe evolved through its early phase transitions. We are living in the aftermath of a series of cosmic law changes that occurred in the first moments of existence. But here's the crucial question: could such phase transitions happen again? Most physicists have assumed that the universe has settled into a stable configuration where no further major transitions are possible. But this assumption might be wrong. The universe might currently exist in what physicists call a metastable state. This is like a ball sitting in a shallow depression on a hillside. The ball is stable for now, but if it gets a big enough push, it could roll down to a much deeper valley, representing a completely different physical state. In quantum field theory, the vacuum of space itself can exist in different energy states. Our universe might currently occupy a false vacuum, a state that appears stable but is actually just temporarily stable. Given enough time or the right trigger, the universe could tunnel to a true vacuum state with completely different physical properties. If this happened, the change would propagate outward at the speed of light in an expanding bubble of new physics. Inside the bubble, the laws of physics would be completely different. Atoms might not be able to exist. The forces that hold matter together might work in entirely new ways. Space and time themselves might have different properties. The terrifying thing about such a transition is that we would have no warning. The bubble of new physics would travel at the speed of light, the fastest that any information can travel. We wouldn't see it coming until it was already here, instantly transforming everything in its path. But perhaps even more unsettling is the possibility that such changes could happen not just once, but repeatedly. The universe might undergo periodic phase transitions, cycling through different sets of physical laws like a cosmic kaleidoscope. Each transition would completely reset the rules of reality, wiping out everything that came before and establishing new possibilities for structure and complexity. Some theoretical physicists have proposed that this kind of cyclical universe might help explain why our current physical laws seem so perfectly tuned for complexity and life to emerge. If the universe repeatedly cycles through different sets of laws, we naturally find ourselves in a phase where the laws happen to allow for observers like ourselves to exist. This idea, sometimes called the landscape multiverse, suggests that there might be an enormous number of possible sets of physical laws, and our universe explores different regions of this landscape over cosmic time. Most of these regions would be sterile, unable to support any kind of complexity or life. But occasionally the universe would stumble into a region where observers could emerge and wonder about the nature of physical law. From this perspective, the laws of physics aren't fundamental truths about reality. They're more like cosmic weather patterns, temporary configurations that happen to prevail in our current cosmic epoch. Just as Earth's weather can change from sunny to stormy, the universe's physical laws might change from life-supporting to sterile and back again over vast timescales. But what could actually trigger such dramatic changes in physical law? One possibility is quantum fluctuations. Even in empty space, quantum mechanics predicts that particles and fields are constantly fluctuating at microscopic scales. Most of these fluctuations are tiny and have no noticeable effect. But very rarely, a quantum fluctuation might be large enough to push the universe from one physical state to another. Another possibility is that the changes are driven by the universe's ongoing expansion and cooling. Just as the early universe underwent phase transitions as it cooled from its initial hot state, continued expansion and cooling might eventually trigger new transitions. The universe might be slowly approaching another critical point where the current physical laws become unstable. Cosmic collisions could also play a role. If our universe exists as part of a larger multiverse, collisions with other universes or regions of different physics might trigger phase transitions. These cosmic crashes could inject enough energy to push local regions of space into new physical states. Perhaps most intriguingly, some theories suggest that consciousness itself might play a role in determining physical law. If the act of observation helps determine the properties of quantum systems, as some interpretations of quantum mechanics suggest, then the presence of observers might help stabilize certain sets of physical laws. The universe might tend to evolve towards states that can support observers, creating a kind of cosmic feedback loop between mind and matter. This brings us to one of the most profound questions in all of science. Are the laws of physics discovered or created? Traditional science assumes we discover pre-existing laws that govern reality. But if the laws can change, and if consciousness plays a role in that change, then perhaps we participate in creating the very laws we think we're discovering. The implications are staggering. If true, it would mean that the universe is not a fixed stage on which the drama of existence plays out, but rather a dynamic, evolving system where the rules of the game can change based on who's playing and how they choose to play. But regardless of what triggers such changes, The possibility that the laws of physics themselves could be rewritten forces us to confront the ultimate impermanence of everything we consider real and solid. Not just individual objects like stars and planets, but the very categories of existence, the fundamental types of particles and forces, the basic structure of space and time. All of these might be temporary features of a universe in constant flux. This doesn't necessarily make existence meaningless, but it does make it far more uncertain and dynamic than we typically imagine. Instead of living in a clockwork universe governed by eternal laws, we might inhabit a cosmic improvisation where the rules are written and rewritten as the performance unfolds. Have such fundamental changes ever actually occurred? The idea that the laws of physics could change might seem like pure speculation, but we actually have direct evidence that such changes have already occurred. In fact, the universe we inhabit today is the product of a series of dramatic transformations in physical law that took place during the first moments after the Big Bang. Understanding these early changes provides crucial insight into how physics might change again in the future. To grasp just how radically different the early universe was, we need to journey back to the very beginning of time itself. In the first instant after the Big Bang, the universe was unimaginably hot and dense. Temperatures exceeded 10 to the 32 degrees Kelvin, billions of times hotter than the core of the Sun. At these extreme conditions, the familiar laws of physics simply didn't apply. The four fundamental forces that govern our current universe, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, were unified into a single superforce. This wasn't just a matter of the forces being very strong and hard to distinguish from each other. They were literally the same force, manifesting as a single unified interaction that has no analog in today's world. Particles as we know them didn't exist. Instead of electrons, protons, neutrons, and photons, there was a seething soup of exotic quantum fields, fluctuating wildly in ways that would be impossible under current physical laws. The very concepts that we use to describe matter and energy had not yet crystallized into their familiar forms. Even space and time themselves were different. The smooth, continuous space-time described by Einstein's general relativity breaks down at the extreme scales and energies present in the first moments after the Big Bang. Quantum effects dominated gravity, creating a foam-like structure where space and time constantly appeared and disappeared in quantum fluctuations. As the universe expanded and cooled, it underwent a series of phase transitions that fundamentally changed how physics worked. These weren't gradual changes, but sudden dramatic transformations that completely rewrote the rules of reality in tiny fractions of a second. The first major transition occurred at approximately 10 to the minus 35 seconds after the Big Bang, when the temperature dropped to about 10 to the 28 degrees Kelvin. At this point, gravity separated from the other forces, becoming the distinct interaction we know today. This separation, called the Planck epoch transition, marked the moment when general relativity began to apply and space-time took on its familiar smooth structure. But the universe was still incredibly alien compared to today. The remaining three forces, electromagnetism and the strong and weak nuclear forces, remained unified in what physicists call the Grand Unified Theory, or GUT force. Under the influence of this unified force, particles behaved in ways that would seem magical by today's standards. The next crucial transition happened at around 10 to the minus 12 seconds, when the temperature fell to approximately 10 to the 15 degrees Kelvin. At this point, the strong nuclear force separated from the electroweak force, which itself was a unified combination of electromagnetism and the weak nuclear force. This transition marked the birth of the strong force that would eventually hold atomic nuclei together. With the strong force now distinct, quarks, the building blocks of protons and neutrons, could begin to exist as separate entities, but they were still confined in a hot, dense plasma, where they couldn't bind together to form the composite particles we see today. The universe was still far too hot and energetic for stable atomic nuclei to exist. The final major force separation occurred much later, at around 10 to the minus 10 seconds, when the temperature dropped to about 100 billion degrees Kelvin. At this point, electromagnetism and the weak nuclear force finally separated into the distinct interactions we observe today. This transition, known as electroweak symmetry breaking, marked the moment when photons, the particles of light, took on their current properties. Each of these transitions was triggered by the universe cooling below a critical temperature. As the temperature dropped, certain symmetries that had been preserved at higher energies were spontaneously broken, leading to the emergence of new, distinct forces with their own characteristic properties and strengths. The process is analogous to what happens when water freezes into ice. At high temperatures, water molecules move freely and randomly in all directions. But as the temperature drops below the freezing point, the molecules suddenly organize themselves into the regular crystal structure of ice. The perfect symmetry of the liquid state is broken, replaced by a more ordered but less symmetric solid state. Similarly, as the early universe cooled, the perfect symmetry of the unified forces was broken, giving rise to the distinct forces with their own specific properties and interaction strengths. But unlike water freezing, these cosmic phase transitions were irreversible and completely transformed the fundamental nature of reality. The evidence for these early transitions comes from multiple sources. High-energy particle accelerators like the Large Hadron Collider at CERN can recreate some of the conditions that existed in the early universe, allowing physicists to study how particles behave at extremely high energies. These experiments have confirmed the unification of electromagnetism and the weak force at high energies, providing direct evidence for electroweak unification. Observations of the cosmic microwave background radiation, the afterglow of the Big Bang, also provide crucial evidence. This radiation carries information about the state of the universe when it was only 380,000 years old, much later than the force unification epoch, but still early enough to preserve signatures of those primordial transitions. The relative abundances of light elements like hydrogen, helium, and lithium produced in the first few minutes after the Big Bang also depend critically on how the fundamental forces behaved during the early epochs. The fact that our observations of these abundances match theoretical predictions based on the standard model of particle physics provides strong confirmation that our understanding of early universe physics is correct. But perhaps the most profound evidence comes from the very existence of matter itself. In the current universe, matter and antimatter annihilate when they come into contact, producing pure energy. If the early universe had contained equal amounts of matter and antimatter, they would have completely annihilated each other, leaving behind a universe filled only with radiation and no matter at all. The fact that we exist proves that there was a slight asymmetry between matter and antimatter in the early universe. This asymmetry, known as baryogenesis, can only be explained by physics beyond the standard model, likely involving processes that occurred during the Grand Unified Theory epoch, when the forces were still unified. The conditions necessary for baryogenesis were first outlined by physicist Andrei Sakharov in 1967. He showed that three conditions must be met: baryon number violation, meaning processes that can create or destroy matter; violation of charge and parity symmetry, meaning the laws of physics are not identical for matter and antimatter; and departure from thermal equilibrium, meaning the universe must be cooling and changing rapidly. All three of these conditions were likely met during the early phase transitions when the fundamental forces separated. The rapidly changing conditions as the universe cooled provided the departure from equilibrium. The exotic physics of the unified forces allowed for baryon number violation. And the symmetry breaking that separated the forces naturally led to differences between matter and antimatter interactions. This means that our very existence is a direct consequence of the changing laws of physics in the early universe. If the forces had remained unified, or if the phase transitions had proceeded differently, matter would never have gained an advantage over antimatter, and the universe would be a cold, empty expanse of radiation with no stars, planets, or life. The early universe also underwent a period of exponential expansion called inflation, which occurred between approximately 10 to the minus 36 and 10 to the minus 32 seconds after the Big Bang. During this brief period, the universe expanded by a factor of at least 10 to the 26th, growing from smaller than a subatomic particle to roughly the size of a grapefruit. Inflation was driven by a special kind of energy field called the inflaton field, which had properties unlike anything that exists in the current universe. This field caused space itself to expand exponentially, stretching quantum fluctuations to macroscopic scales and creating the seeds that would eventually grow into galaxies and large-scale cosmic structures. The physics governing inflation were fundamentally different from the physics we observe today. The inflaton field had to have very specific properties, including the ability to maintain a nearly constant energy density even as space expanded exponentially. No known field in the current universe behaves this way, suggesting that the laws governing matter and energy were radically different during the inflationary epoch. When inflation ended, the inflaton field decayed, releasing its stored energy and reheating the universe to extremely high temperatures. This process, called reheating, populated the universe with the particles and radiation that would go on to form the matter we see today. But the transition from the inflationary epoch to the radiation-dominated epoch that followed represented another fundamental change in how physics worked. These early transitions had consequences that persist to this day. The relative strengths of the fundamental forces, which were determined by how they separated during the phase transitions, control everything from the stability of atomic nuclei to the rate of stellar burning to the expansion rate of the universe itself. The fine structure constant, which governs electromagnetic interactions, has the value it does because of how electromagnetism separated from the weak force during electroweak symmetry breaking. If this transition had proceeded slightly differently, atoms might not be stable, chemistry might not work, and life, as we know it, would be impossible. Similarly, the strength of the strong nuclear force, which determines how tightly protons and neutrons bind together in atomic nuclei, was set during the separation of the strong force from the electro-weak force. A slightly different transition could have resulted in a universe where atomic nuclei are either too weakly bound to be stable, or so tightly bound that they can't undergo the nuclear reactions that power stars. Even the rate of cosmic expansion, which is controlled by the interplay between gravity and dark energy, may have been influenced by the early phase transitions. Some theories suggest that dark energy itself is a remnant of the fields that drove inflation, or participated in the force unification processes. This raises a profound question about the nature of physical law. Are the specific values of the fundamental constants and the particular forms of the physical laws simply accidents of how the early phase transitions happen to unfold? Or is there some deeper principle that required physics to evolve in exactly the way it did? Some physicists argue for the anthropic principle, the idea that the laws of physics must be compatible with the existence of observers like ourselves, simply because we're here to observe them. From this perspective, the early phase transitions unfolded in the specific way they did, because any other outcome would have resulted in a universe incapable of supporting life and consciousness. But this raises even deeper questions. If the phase transitions could have proceeded differently, creating different sets of physical laws, what determined which path was actually taken? Was it pure chance? Or were there guiding principles that we don't yet understand? The possibility that consciousness itself plays a role in determining physical law adds another layer of mystery. Some interpretations of quantum mechanics suggest that observation, plays a fundamental role in determining the properties of quantum systems. If this is true, then the presence of observers might influence the evolution of physical law itself. But regardless of the ultimate explanation, the historical evidence is clear. The laws of physics have changed before and changed dramatically. The universe we inhabit today is the product of a series of spontaneous transformations that completely rewrote the rules of reality in the first moments after the Big Bang. This historical precedent makes the possibility of future changes far more plausible. If physics could change once, transforming a universe of unified forces into the complex structured cosmos we observe today, then it could potentially change again. The question is not whether such changes are possible, but when and how they might occur. The early universe provides a template for understanding how dramatic changes in physical law can unfold. They happen suddenly, during phase transitions triggered by changing conditions. They are irreversible, completely transforming the nature of reality. And they can have consequences that persist for billions of years, shaping the entire subsequent evolution of the cosmos. But there's one crucial difference between the early universe and today. The early changes happened during a period of rapid cooling and expansion, when the universe was far from equilibrium and energy densities were enormous. Today's universe is much colder, more dilute, and closer to equilibrium. The question is whether these more stable conditions make future phase transitions impossible, or whether they simply make them rarer and harder to predict. If laws changed before, can they change again? We've seen how the laws of physics underwent dramatic transformations in the early universe, but those changes led to new, stable configurations that have persisted for nearly 14 billion years. But what if the next change is different? What if instead of evolving into a new stable state, the laws of physics could simply end, leaving behind a universe where the very concept of physical law becomes meaningless? This isn't idle speculation. Some of the most respected physicists in the world have developed detailed theories describing exactly how the fundamental structure of reality could collapse entirely. These scenarios, grounded in rigorous mathematics and supported by experimental evidence, paint a picture of cosmic destruction so complete that it makes the death of individual stars or even galaxies seem trivial by comparison. The most thoroughly studied mechanism for the complete breakdown of physics is called vacuum decay, or false vacuum collapse. To understand this process, we need to think about the vacuum of space not as empty nothingness, but as a dynamic quantum field that can exist in different energy states. In quantum field theory, even completely empty space is filled with quantum fields fluctuating at their lowest possible energy levels. These vacuum fluctuations are not just theoretical constructs. They have measurable effects, like the Casimir force, which has been experimentally verified in laboratories around the world. The vacuum state represents the ground state of all quantum fields, the configuration with the lowest possible total energy. But here's the terrifying possibility. What we think of as the vacuum might not actually be the true ground state. Our universe might exist in what physicists call a false vacuum, a state that appears stable but is actually just metastable, like a ball sitting in a shallow valley on a hillside. The ball seems stable, but if it gets nudged hard enough, it will roll down to a much deeper valley, representing a state of much lower energy. If the universe exists in a false vacuum, then it could potentially tunnel to a true vacuum state through a quantum mechanical process. This tunneling would begin at a single point in space, creating a bubble of true vacuum that expands outward at the speed of light. Inside this bubble, the laws of physics would be completely different from what we observe today. The physics inside a true vacuum bubble would be so alien that our current concepts of matter, energy, space, and time might not even apply. Atoms as we know them could not exist. The forces that hold matter together might be completely absent. Even the dimensionality of space itself might be different, with the familiar 3 dimensions of space plus 1 of time replaced by some other configuration entirely. Sidney Coleman and Frank DeLucia worked out the mathematical details of this process in 1977. Their calculations show that if the universe exists in a false vacuum, bubble nucleation is not just possible but inevitable. Quantum fluctuations will eventually create a bubble of true vacuum somewhere in the universe, and once that happens, nothing can stop its expansion. The bubble wall would travel at exactly the speed of light, which means we would have no warning of its approach. Light from the advancing bubble wall would reach us at the same instant as the wall itself. One moment, we would be living in a universe governed by familiar physical laws, and the next moment, everything would be transformed into something completely unrecognizable. But would we even survive the transition? Almost certainly not. The energy difference between the false vacuum and true vacuum would be released as the bubble wall passed through, creating temperatures and energy densities comparable to those in the first moments after the Big Bang. Any complex structures like atoms, molecules, planets, stars, or living beings would be instantly vaporized. Even if somehow matter could survive the transition, it would find itself in a universe with completely different physical laws. The forces that allow atoms to exist might be absent. The electromagnetic interactions that make chemistry possible might work in entirely different ways. The gravitational attraction that holds planets in orbit around stars might be replaced by some other form of interaction entirely. The Higgs field, which gives particles their masses through the Higgs mechanism, provides a concrete example of how vacuum decay could occur. The Higgs field currently sits at a particular value throughout all of space, but calculations suggest this might not be the lowest possible energy configuration. If the Higgs field were to tunnel to a lower energy state, it would change the masses of all fundamental particles. Such a transition would be catastrophic. Protons and neutrons would suddenly have different masses, destabilizing every atomic nucleus in the universe. Electrons would have different masses, completely altering the structure of atoms and molecules. The fundamental particles that make up our bodies and everything around us would no longer be able to form stable structures. Recent measurements of the Higgs boson mass at the Large Hadron Collider have only added to these concerns. The measured value of 125 billion electron volts is tantalizingly close to the boundary between a stable and metastable vacuum. Small uncertainties in the measurement or the discovery of new physics beyond the standard model could push the calculation either way. If the Higgs vacuum is indeed metastable, then vacuum decay becomes not just a theoretical possibility, but a genuine threat. The timescale for such decay is extraordinarily long, potentially much longer than the current age of the universe, but it's not infinite. Eventually, quantum fluctuations would trigger the transition, and the bubble of true vacuum would begin its inexorable expansion across the cosmos. But vacuum decay isn't the only way the laws of physics could end completely. Another possibility is a cosmological phase transition driven by the continued expansion and cooling of the universe. Just as the early universe underwent phase transitions as it cooled from its initial hot state, the ongoing expansion might eventually trigger new transitions that fundamentally alter the nature of physical law. These late-time phase transitions could be triggered by dark energy, the mysterious force causing the acceleration of cosmic expansion. If dark energy is not truly constant but instead evolves over cosmic time, it might eventually reach values that destabilize the current configuration of physical law. Some models of dark energy, called quintessence models, involve a slowly evolving scalar field that changes over billions of years. If this field were to reach a critical value, it could trigger a phase transition that completely rewrites the laws of physics. Unlike vacuum decay, which spreads at the speed of light, Such a transition might occur simultaneously throughout the universe, instantly transforming all of reality. The Big Rip scenario represents another way that physics could effectively end. In this model, the acceleration of cosmic expansion continues to increase over time, eventually becoming so rapid that it overcomes all the forces holding matter together. First, galaxies would be torn apart as the expansion overcomes gravitational attraction. Then solar systems would disintegrate as space expands faster than light can travel between planets and stars. Eventually, the acceleration would become so extreme that it would overcome the strong nuclear force holding atomic nuclei together, and even the electromagnetic forces binding electrons to atoms. Matter would be shredded down to its fundamental constituents, leaving behind a universe of isolated particles flying apart at ever-increasing speeds. In the final moments before the Big Rip, even space and time themselves would be torn apart. The fabric of space-time would be stretched so rapidly that causality would break down. The very concepts of distance and duration would lose their meaning as the universe literally tears itself apart at the most fundamental level. The timescale for a Big Rip depends on the precise properties of dark energy, but some models predict it could occur in as little as 20 billion years from now. This might seem like an impossibly long time, but it's less than twice the current age of the universe. If such models are correct, we're already living in the second half of the universe's existence. Another mechanism for the complete breakdown of physics involves the spontaneous decay of protons, the building blocks of atomic nuclei. Grand unified theories predict that protons are not actually stable, but decay with an extraordinarily long half-life, possibly around 10 to the 34 years. If protons do decay, then all atomic nuclei will eventually disintegrate, regardless of what happens to the large-scale structure of the universe. Stars, planets, and all matter as we know it would gradually dissolve into a sea of electrons, positrons, neutrinos, and photons. The complex chemistry that makes life possible would become impossible as the atoms that make up molecules slowly vanish. Even more exotic possibilities arise from string theory and other attempts to unify quantum mechanics with general relativity. These theories suggest that space itself might have additional dimensions beyond the three we directly experience. If these extra dimensions were to change size or configuration, it could completely alter the laws of physics in our three-dimensional slice of reality. Some string theory models predict that the extra dimensions are not fixed, but can evolve over time. If they were to suddenly expand or contract or change their geometric configuration, the fundamental constants and even the basic forms of physical law could be completely transformed. What we experience as particles and forces might be revealed as mere shadows of higher dimensional objects and interactions. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, raises even more radical possibilities. If reality is indeed holographic, then what we perceive as three-dimensional physics might be an emergent phenomenon arising from more fundamental two-dimensional processes. Changes in the boundary physics could cause the entire three-dimensional illusion to collapse or transform. Perhaps most unsettling of all is the possibility that the laws of physics could end not through any physical process, but through a logical or mathematical inconsistency that makes them self-contradictory. Gödel's incompleteness theorems show that any sufficiently complex mathematical system contains statements that cannot be proven true or false within the system itself. If the laws of physics are mathematical in nature, as many physicists believe, then they too might be subject to Gödel's limitations. It's conceivable that the universe could evolve into a state where the mathematical relationships describing physical law become self-contradictory, causing the entire framework of physics to collapse into logical incoherence. The implications of any of these scenarios are almost impossible to comprehend. We're not talking about the end of human civilization, or even the end of life in the universe. we're talking about the end of the very possibility of existence itself. If the laws of physics cease to operate, then the categories we use to understand reality, matter, energy, space, time, cause, and effect would all become meaningless. Yet these aren't science fiction fantasies, but serious scientific hypotheses based on our best current understanding of fundamental physics. The mathematics describing vacuum decay has been worked out in detail. The observational evidence for accelerating cosmic expansion that could lead to a big rip is overwhelming. The theoretical framework suggesting proton decay or extra-dimensional instabilities are taken seriously by researchers around the world. This doesn't mean any of these scenarios will actually occur. The universe might exist in a perfectly stable, true vacuum. Dark energy might be truly constant, preventing runaway acceleration. Protons might be absolutely stable, never decaying no matter how long we wait. The extra dimensions suggested by string theory might be permanently fixed in their current configuration. But the mere fact that such scenarios are theoretically possible forces us to confront the ultimate fragility of existence. Everything we consider real and permanent, from atoms to galaxies to the laws of logic themselves, might be temporary features of a universe that could transform or disappear entirely without warning. The search for signs of impending vacuum decay or other cosmic catastrophes has become an active area of research. Astronomers scan the skies for anomalous regions that might indicate expanding bubbles of different physics. Particle physicists study the properties of the Higgs field to determine whether our vacuum is truly stable. Cosmologists analyze the cosmic microwave background for signs of ancient phase transitions that might hint at future instabilities. So far, no definitive evidence for cosmic instability has been found, but the absence of evidence is not evidence of absence. A vacuum decay event could be approaching us right now at the speed of light, and we would have no way of detecting it until it arrived. The Big Rip could be destined to occur in 20 billion years. But we might not be able to confirm this until dark energy evolution becomes more pronounced. Living with this uncertainty requires a fundamental shift in how we think about existence and meaning. If the laws of physics could end at any moment, does anything we do really matter? Or does the very fragility of existence make every moment more precious, every achievement more remarkable? Perhaps the possibility that physics itself could end is the ultimate reminder of how extraordinary it is that we exist at all. In a universe where the very foundations of reality are temporary and fragile, the emergence of complexity, life, and consciousness becomes not just remarkable, but almost miraculous. But could we detect such changes before they happen? If the laws of physics are indeed temporary and subject to change, one of the most crucial questions becomes whether we could detect such changes before they fundamentally alter or destroy our reality. The answer depends on what type of change we're dealing with, how fast it occurs, and whether it provides any advance warning before transforming the universe as we know it. For gradual changes in fundamental constants, we actually have a fighting chance. These slow drifts leave signatures that can be detected through careful astronomical observations and precision laboratory measurements. The key insight is that light carries information about the physical conditions at the time and place it was emitted, creating a cosmic archaeological record that spans billions of years. When we observe distant quasars, we're seeing light that has traveled for enormous periods of time to reach us. This ancient light bears the fingerprints of the fundamental constants that were operating when it was first emitted. By comparing the spectral lines in this ancient light with the same transitions measured in laboratories today, astronomers can detect tiny changes in constants, like the fine structure constant over cosmic time. The most sensitive searches use what are called many-multiplet methods, which compare the wavelengths of different atomic transitions that have varying sensitivities to changes in fundamental constants. If the fine structure constant has changed over time, these different transitions will shift by different amounts. creating a characteristic pattern that can be distinguished from other effects like cosmological redshift or instrumental errors. Current observations using the world's largest telescopes can detect changes in the fine structure constant as small as a few parts per million over billions of years. Future telescopes, like the extremely large telescope currently under construction in Chile, will push this sensitivity even further, potentially detecting changes as small as parts per billion. Laboratory experiments provide another avenue for detecting changing constants, though over much shorter timescales. Atomic clocks, which are among the most precise instruments ever built, can detect changes in fundamental constants by comparing the frequencies of different atomic transitions over periods of months or years. The most advanced atomic clocks can measure frequencies with uncertainties of less than 1 part in 10 to the 18th. By comparing clocks based on different atoms or different transitions within the same atom, physicists can search for time variations in the fine structure, constant, the electron-to-proton mass ratio, and other fundamental parameters. These laboratory searches have the advantage of being conducted in controlled conditions with well-understood systematic effects, but they can only probe changes occurring over human timescales. A constant that drifts over millions of years would be completely undetectable in a laboratory experiment lasting a few years. Geophysical searches offer a middle ground between astronomical and laboratory methods. The Oklo Natural Nuclear Reactor in Gabon, Africa, operated about 2 billion years ago, when uranium concentrations were high enough to sustain a chain reaction. The byproducts of this ancient reactor preserve information about the fundamental constants that governed nuclear physics 2 billion years ago. By analyzing the isotope ratios in the reactor remnants, physicists can infer the values of constants like the fine structure constant when the reactor was operating. These measurements suggest that the fine structure constant has changed by less than 1 part in 10 to the 7th over the past 2 billion years, providing important constraints on theories that predict slowly varying constants. Similar constraints come from studying the decay products of long-lived radioactive isotopes in meteorites and ancient rocks. These cosmic clocks record the values of fundamental constants over geological timescales, bridging the gap between laboratory experiments and astronomical observations. But detecting gradual changes in constants is the easy case. Far more challenging would be detecting the approach of a sudden phase transition that could completely rewrite the laws of physics. In many scenarios, such transitions would provide little or no advance warning. Vacuum decay represents the most terrifying example. If our universe exists in a false vacuum, the transition to a true vacuum state would propagate outward at the speed of light from the point where it first occurs. Since information cannot travel faster than light, we would receive no warning of the approaching change until it was already upon us. However, there might be some indirect signatures we could look for. The region of space where vacuum decay first occurs might exhibit unusual properties in the time leading up to the transition. High-energy cosmic ray interactions or other extreme astrophysical events might occasionally probe energy scales high enough to trigger metastability, potentially creating small, short-lived bubbles of different vacuum states. These transient bubbles would quickly collapse back to our current vacuum state, but they might leave detectable signatures in the form of unusual particle emissions or gravitational wave signals. Advanced gravitational wave detectors like LIGO and Virgo are already sensitive enough to detect some types of vacuum decay events, though the signals would be extremely difficult to distinguish from other astrophysical sources. The Large Hadron Collider and other particle accelerators provide another way to probe vacuum stability. By colliding particles at the highest energies achievable on Earth, these experiments can explore the behavior of the Higgs field and other fundamental fields under extreme conditions. If our vacuum is metastable, there's a tiny possibility that high-energy collisions could trigger a vacuum decay event. This possibility generated considerable controversy when the LHC was first being planned, with some critics arguing that the experiments posed an existential risk to humanity. However, detailed calculations showed that the energies involved, while enormous by human standards, are far lower than those routinely produced by cosmic ray interactions in the upper atmosphere. If cosmic rays haven't triggered vacuum decay over the billions of years they've been bombarding Earth, then human-built accelerators operating at much lower energies are extremely unlikely to do so. Nevertheless, each new generation of particle accelerators pushes deeper into unexplored energy regimes, potentially probing closer to any instabilities that might exist. Cosmological phase transitions driven by evolving dark energy might provide more warning than vacuum decay. If dark energy is not truly constant but evolves according to some dynamical field, changes in its properties might be detectable through precision measurements of cosmic expansion. The most sensitive probes involve observations of Type 1a supernovas, which serve as standard candles for measuring cosmic distances. By observing supernovas at different redshifts, astronomers can trace the expansion history of the universe and detect any changes in the acceleration rate over time. Current supernova surveys can detect changes in dark energy properties over the past several billion years, but future surveys will be far more sensitive. The Large Synoptic Survey Telescope, set to begin operations in the mid-2020s, will observe millions of supernovas and other distance indicators, providing unprecedented precision in mapping cosmic expansion. If dark energy is evolving toward a phase transition that could alter the laws of physics, these surveys might detect the early stages of that evolution, potentially providing centuries or millennia of advance warning. However, this assumes that the transition occurs gradually rather than suddenly, and that the changes in expansion rate precede rather than accompany the fundamental alterations in physical law. Gravitational wave astronomy opens up entirely new possibilities for detecting exotic physics. The merger of black holes and neutron stars produces gravitational waves that carry information about the fundamental properties of space, time, and gravity. Any modifications to Einstein's general relativity, whether from extra dimensions, modified gravity theories, or incipient phase transitions, could potentially be detected through precision gravitational wave observations. The current generation of gravitational wave detectors has already confirmed that gravitational waves propagate at the speed of light, and that their polarization properties match Einstein's predictions. Future detectors, including space-based missions like LISA, will be sensitive enough to detect much more subtle deviations from general relativity. If the laws of physics are beginning to change, gravitational waves might provide the first evidence. Space and time themselves are the most fundamental aspects of physical law, so any incipient breakdown in the structure of space-time might be detectable through gravitational wave observations before it becomes apparent through other means. The cosmic microwave background radiation provides a snapshot of the universe when it was only 380,000 years old, preserving information about physical conditions in the early cosmos. While this radiation primarily tells us about the past rather than the future, it might contain clues about the long-term stability of physical law. Detailed analysis of the microwave background has revealed tiny fluctuations that reflect quantum fluctuations from the inflationary epoch, magnified to cosmic scales. These fluctuations might preserve signatures of phase transitions or other exotic physics from the very early universe, potentially providing insights into whether similar transitions could occur in the future. Advanced analysis techniques, including machine learning algorithms trained to recognize subtle patterns in the data, are revealing increasingly detailed information about early universe physics. Future missions with improved sensitivity and resolution might detect signatures of metastable vacuums, extra dimensions, or other exotic physics that could be relevant to the long-term evolution of physical law. Neutrino astronomy represents another frontier for detecting exotic physics. Neutrinos interact so weakly with matter that they can travel across the entire universe virtually unimpeded, carrying information about conditions in the most extreme astrophysical environments. If fundamental constants or physical laws are changing in remote regions of the universe, neutrinos produced in those regions might carry signatures of the altered physics. Large underground neutrino detectors like IceCube in Antarctica are already sensitive enough to detect neutrinos from distant sources, and future detectors will have even greater sensitivity and better directional resolution. The most challenging detection problem involves changes that occur too quickly for any warning or too universally for any comparison. If a phase transition were to occur simultaneously throughout the universe, transforming all of physical law instantaneously, there would be no way to detect it in advance and possibly no way to recognize it, even after it occurred. In such a scenario, any observers who survived the transition would find themselves in a universe with completely different physical laws. They might not even retain memories of the previous state, as the neural processes underlying memory and consciousness might not be possible under the new physics. The change could be so fundamental that the very concept of detection or observation becomes meaningless. But even in less extreme scenarios, detection might be impossible for practical reasons. If a vacuum decay bubble were approaching from a distant galaxy, we might in principle be able to detect its effects on intervening matter and radiation. However, the timescale for detection might be so short that there would be no opportunity to take any meaningful action. Consider a vacuum decay event occurring in the Andromeda Galaxy, our nearest major galactic neighbor. The bubble would take about 2.5 million years to reach us, traveling at the speed of light. This might seem like plenty of time to prepare, but the signatures of the approaching bubble might only become detectable when it's much closer, perhaps only years or decades before arrival. Moreover, what could we possibly do with such information? There's no way to stop or deflect a vacuum decay bubble. We couldn't evacuate to another galaxy, as the bubble would eventually encompass the entire observable universe. The only possible response might be to try to preserve some record of our civilization and knowledge, though even this would be futile if the new vacuum state couldn't support any form of information storage. The psychological and social implications of detecting an approaching end to physics would be unprecedented. Unlike natural disasters or even extinction-level asteroid impacts, which threaten life but leave the universe itself intact, the end of physical law would threaten the very possibility of existence. How would human society respond to the certain knowledge that reality itself has an expiration date? On the other hand, false alarms could be equally disruptive. Given the enormous consequences of such a detection, the standards of evidence would need to be extraordinarily high. Multiple independent confirmations using different observational techniques would be essential. Even then, the possibility of systematic errors or misinterpretation would need to be carefully considered. The scientific community has already grappled with similar issues on a smaller scale. The initial detection of faster-than-light neutrinos by the OPERA experiment in 2011 caused enormous excitement and concern before being traced to a loose fiber optic cable. The recent detection of a possible signal from Proxima Centauri by the Breakthrough Listen project generated speculation about extraterrestrial intelligence before being attributed to terrestrial interference. For something as consequential as the impending end of physical law, the verification process would need to be even more rigorous. International collaboration would be essential, with multiple research groups using different instruments and analysis techniques to confirm any claimed detection. The process might take years or decades, during which time the approaching change might accelerate or alter in unpredictable ways. Perhaps the most we can hope for is to develop increasingly sensitive methods for detecting changes in physical law, while simultaneously working to understand the theoretical frameworks that predict such changes. Even if we cannot prevent the end of physics, we might at least achieve a deeper understanding of why it occurs and what it might tell us about the deeper nature of reality. The search for changing physical laws represents one of the most fundamental challenges in science. It requires pushing our observational capabilities to their absolute limits, while simultaneously grappling with theoretical concepts that challenge our basic assumptions about the nature of existence. Whether we succeed in detecting such changes may ultimately determine whether humanity faces the end of physics as informed observers or as victims of cosmic forces beyond our comprehension. But what philosophical and scientific implications would this carry? The possibility that the laws of physics are temporary rather than eternal doesn't just challenge our scientific understanding of the universe. It fundamentally undermines some of our deepest philosophical assumptions about the nature of reality, knowledge, and existence itself. If physical laws can change, then everything we thought we knew about the permanence and reliability of the natural world must be reconsidered. For over 3 centuries, since the time of Isaac Newton, science has been built on the assumption that nature operates according to unchanging mathematical laws. This assumption, often called the principle of uniformity, holds that the same physical laws that operate here and now have operated everywhere and everywhen throughout cosmic history. It's what allows us to study distant stars and ancient geological formations, confident that they follow the same rules as objects in our laboratories. But if the laws of physics are temporary, then this foundational assumption crumbles. Instead of discovering eternal truths about the universe, science becomes an exercise in mapping the current local rules of a cosmic game that could change at any moment. The laws we've spent centuries uncovering might be no more permanent than weather patterns, temporary configurations that happen to prevail in our particular cosmic epoch. This shift in perspective is so profound that it challenges the very meaning of scientific knowledge. When we say that energy is conserved, or that nothing can travel faster than light, or that gravitational attraction decreases with the square of distance, are we stating eternal truths about reality? Or are we simply describing the temporary rules that happen to govern our current cosmic environment? The distinction matters enormously for how we understand the relationship between human knowledge and cosmic reality. Traditional science assumes we're gradually uncovering the permanent architecture of the universe piece by piece, building a complete picture that will remain valid forever. But if physical laws are temporary, then our scientific theories are more like weather reports, accurate descriptions of current conditions that could become obsolete without warning. This doesn't necessarily make scientific knowledge less valuable, but it does make it more humble and provisional. Instead of seeking eternal truths, science becomes an ongoing effort to understand the present state of cosmic evolution. Our theories would be snapshots of temporary physical configurations rather than timeless descriptions of permanent reality. The implications extend far beyond academic philosophy. The entire technological civilization we've built depends on the assumption that physical laws are reliable and permanent. Every bridge, computer, spacecraft, and medical device is designed based on our current understanding of physics. If those laws could change, then all of our technology becomes potentially obsolete, possibly catastrophically so. Consider something as basic as the internal combustion engine. It works because we understand the chemistry of fuel combustion, the thermodynamics of expanding gases, and the materials science of metal alloys under stress. But if the fundamental constants governing atomic structure were to shift, chemical reactions might proceed differently. Thermodynamic relationships might change, and materials might have completely different properties. Our entire approach to engineering and technology assumes that the physical principles we've learned will continue to apply indefinitely into the future. We design nuclear power plants to operate safely for decades, build bridges to last for centuries, and launch space missions that will travel for years or even decades before reaching their destinations. All of these endeavors implicitly assume that the laws of physics will remain constant throughout their operational lifetimes. If physical laws are temporary, then this assumption could be fatally flawed. A space probe launched today might encounter regions of space where physics works differently, or the laws governing its operation might change during its journey. A nuclear reactor designed for today's physics might become unstable if fundamental constants drift over time. The economic implications are equally staggering. The entire global economy is built on the assumption that we can make reliable predictions about how physical systems will behave. We invest billions of dollars in infrastructure projects, sign long-term contracts for energy production, and make financial commitments based on our understanding of how the physical world works. If the laws of physics are subject to change, then all long-term planning becomes fundamentally uncertain. How do you calculate the return on investment for a solar power plant if the fundamental constants governing photovoltaic conversion might change? How do you design a pension system if the physical processes underlying human aging and longevity might be altered by changing physics? But perhaps the most profound implications are existential and spiritual. The idea of unchanging physical laws has provided a sense of cosmic stability and order that many people find deeply comforting. Even in a chaotic and unpredictable world, there was always the underlying assurance that the fundamental structure of reality remained constant. If physical laws are temporary, then this bedrock of stability disappears. We find ourselves not just in a universe that is vast and possibly meaningless, but in one where the very rules of existence are subject to change without notice. The cosmos becomes not just indifferent to human concerns, but actively unstable at the most fundamental level. This realization forces us to confront the ultimate contingency of existence, not just our lives, our civilization, or even our species, but the very categories of being that make existence possible might be temporary features of a universe in constant flux. Matter, energy, space, time, cause and effect, all of these might be provisional arrangements that could be revised or abolished by cosmic processes beyond our control or comprehension. Yet this same realization might also be liberating. If the laws of physics are not eternal constraints but temporary conditions, then perhaps reality is far more open and creative than we imagined. Instead of being trapped within the rigid confines of unchanging natural law, we might inhabit a universe of infinite possibility, where new forms of existence and experience could emerge as physical laws evolve. The relationship between consciousness and physical law becomes particularly intriguing in this context. Some interpretations of quantum mechanics suggest that consciousness plays a fundamental role in determining the properties of physical systems. If this is true, then the presence of conscious observers might influence the evolution of physical law itself. From this perspective, the universe might not be a passive stage on which consciousness appears, but rather an active collaboration between mind and matter. The laws of physics might evolve in response to the presence and activities of conscious beings, creating a cosmic feedback loop where consciousness shapes the very reality it observes. This possibility raises profound questions about the relationship between knowledge and reality. If consciousness influences physical law, then our scientific observations might not be neutral recordings of objective facts, but active participations in the creation of reality. The very act of studying the universe might help determine what kind of universe we inhabit. The implications for free will and moral responsibility are equally complex. If physical laws are deterministic and unchanging, then every event, including human actions, is in principle predictable from prior conditions. But if physical laws can change, then the future becomes fundamentally open, possibly allowing for genuine choice and moral agency. On the other hand, If physical laws change randomly or according to processes beyond human understanding, then human actions might become meaningless in a different way. What's the point of moral behavior if the very categories of right and wrong might be abolished by a cosmic phase transition? These philosophical challenges become even more complex when we consider the possibility of multiple observers with different relationships to changing physical laws. If consciousness does influence physical law, then different types of conscious beings might experience different versions of reality. The universe might fragment into multiple domains with different physical laws, each shaped by the particular forms of consciousness that inhabit them. The question of meaning becomes particularly acute in a universe with temporary physical laws. Traditional approaches to meaning often rely on the assumption that there are stable truths or values that transcend individual existence. But if even the most fundamental aspects of reality are subject to change, then all claims to universal meaning become suspect. Yet perhaps this very uncertainty creates new opportunities for meaning. If reality is genuinely open and creative, then conscious beings might play a role in shaping not just their own destinies, but the fundamental character of existence itself. Instead of discovering pre-existing meaning, we might participate in creating the meaning that the universe comes to embody. The relationship between scientific and religious worldviews also requires reconsideration. Traditional religion often emphasizes the eternal and unchanging nature of divine reality, while science has sought eternal laws governing natural phenomena. But if physical laws are temporary, then both scientific and religious certainties are called into question. Some might see temporary physical laws as evidence for a more dynamic and creative divine reality, one that continuously creates and recreates the universe rather than establishing it once and for all. Others might see it as evidence against any form of cosmic order or purpose, suggesting that existence is fundamentally arbitrary and chaotic. The implications for human identity are equally profound. We typically think of ourselves as biological entities governed by the laws of chemistry and physics. But if those laws can change, then human nature itself becomes contingent and potentially transformable. We might not be fixed biological entities, but dynamic processes that could be fundamentally altered by changes in physical law. This possibility is both terrifying and exciting. Terrifying because it suggests that everything we consider essential to human nature might be temporary and subject to cosmic forces beyond our control. Exciting because it suggests that human potential might be far greater than we currently imagine, limited only by the particular configuration of physical laws that happens to prevail in our cosmic epoch. The relationship between individual and collective existence also becomes more complex. If physical laws can change, then the boundary between self and environment becomes more fluid. Changes in fundamental constants might alter not just the external world, but the internal processes of consciousness and identity. Perhaps most challenging of all is the question of how to live with such radical uncertainty. If everything we consider real and stable might be temporary, how do we make decisions, form relationships, or commit to long-term goals? How do we maintain hope and motivation in the face of such cosmic instability? One response might be to embrace the uncertainty as a fundamental aspect of existence. Instead of seeking security in permanent truths, we might learn to find meaning in the very process of creative becoming that characterizes a universe with changing physical laws. The temporary nature of existence might make each moment more precious rather than less meaningful. Another response might be to focus on what remains constant, even if physical laws change. Perhaps consciousness itself, or the capacity for experience and relationship, persists through physical transformations. Perhaps there are deeper patterns or principles that remain stable, even as surface phenomena change. The possibility of temporary physical laws also raises questions about the relationship between knowledge and wisdom. Scientific knowledge, which seeks to understand how things work, becomes more provisional and limited. But wisdom, which seeks to understand how to live well, might become more important as we learn to navigate fundamental uncertainty. Perhaps the deepest implication is that temporary physical laws force us to take responsibility for our existence in a new way. If reality is not fixed but evolving, and if consciousness might play a role in that evolution, then we become not just observers of the universe, but participants in its ongoing creation. This participation might occur through our scientific investigations, which probe the boundaries of physical law and potentially influence its evolution. It might occur through our technological activities, which create new forms of organization and complexity. It might occur through our moral and spiritual practices, which express our deepest values about what kind of universe we want to inhabit. In the end, the possibility of temporary physical laws challenges us to embrace both the terror and the wonder of genuine cosmic creativity. We might inhabit not a finished universe governed by eternal laws, but a universe still in the process of becoming, where the very nature of reality remains open to transformation. This vision of reality is simultaneously more fragile and more hopeful than the traditional scientific worldview. More fragile because nothing is guaranteed to persist, not even the basic categories of existence. More hopeful because genuine novelty and creativity remain possible, even at the most fundamental levels of reality. Whether this possibility represents the collapse of human knowledge and meaning, or their ultimate liberation, depends largely on how we choose to respond to the challenge. The universe with temporary physical laws might be terrifying chaos or creative freedom, cosmic meaninglessness or infinite possibility. So what can we safely and conclusively summarize scientifically? After exploring the theoretical possibilities and philosophical implications of temporary physical laws, we must confront a crucial question. How likely is any of this to actually occur? Are we dealing with genuine scientific predictions based on solid evidence? Or are these merely speculative scenarios that make for interesting thought experiments but have little bearing on reality? The honest answer is that we're operating in a realm where established science meets the frontiers of theoretical speculation. Some aspects of temporary physics rest on solid observational foundations, while others remain highly speculative. Understanding where the boundary lies between confirmed science and educated guesswork is essential for evaluating how seriously we should take these possibilities. Let's start with what we know for certain. The historical evidence for changing physical laws in the early universe is overwhelming and undisputed. The phase transitions that separated the fundamental forces, the period of cosmic inflation, and the symmetry-breaking processes that gave particles their current masses are all well-established aspects of modern cosmology. These changes fundamentally altered how physics worked, transforming a universe of unified forces into the complex, structured cosmos we observe today. This historical precedent is crucial because it proves that dramatic changes in physical law are not just theoretically possible, but have actually occurred. The universe has already undergone the kind of fundamental transformations that we're considering for the future. The laws of physics that govern our current epoch are demonstrably not eternal, but emerged from earlier, very different configurations. The evidence for these early changes comes from multiple independent sources. Particle accelerator experiments have directly confirmed the unification of electromagnetism and the weak nuclear force at high energies, providing laboratory verification of early universe physics. Observations of the cosmic microwave background radiation preserve detailed information about conditions when the universe was only 380,000 years old, including signatures of earlier phase transitions. The abundance of light elements produced in the first few minutes after the Big Bang matches theoretical predictions based on our understanding of how the fundamental forces separated and evolved. Even the existence of matter itself, rather than a universe of pure radiation, requires the kind of symmetry-breaking processes that characterize the early cosmic phase transitions. So we know with certainty that the laws of physics have changed before and changed dramatically. The question is whether such changes could happen again and what form they might take. The evidence for ongoing changes in fundamental constants is much more ambiguous. The studies of distant quasar light that suggest possible variations in the fine structure constant over cosmic time represent genuine scientific observations, but they remain controversial and disputed. Some research groups report detecting variations at the level of a few parts per million over billions of years, while others find no evidence for any changes at all. The controversy arises partly from the extreme precision required for these measurements. The claimed variations are so small that they push current observational techniques to their absolute limits. Systematic errors in the instruments, uncertainties in the analysis methods, and contamination from other astrophysical effects could potentially mimic or mask the subtle signatures of changing constants. Moreover, even if some measurements do show evidence for varying constants, the significance of these variations remains unclear. A change of a few parts per million over billions of years is enormous from the perspective of fundamental physics, but it's also slow enough that it would have negligible practical consequences over human timescales. The theoretical frameworks that predict changing constants are similarly mixed in their scientific status. String theory, which naturally accommodates varying fundamental parameters, is mathematically sophisticated and addresses many deep problems in physics, but it has yet to make any confirmed experimental predictions. The theory remains largely untested by observation, making it difficult to assess how seriously we should take its predictions about changing physical laws. Quantum field theory does allow for the possibility that fundamental constants could evolve over time, particularly through interactions with scalar fields or other exotic matter. However, most realistic models predict that any such evolution would be extraordinarily slow, occurring over timescales much longer than the current age of the universe. The status of vacuum stability calculations is particularly important because they directly address whether our universe could undergo a catastrophic phase transition. The calculations depend critically on precise measurements of particle masses and coupling constants, particularly those associated with the Higgs boson and the top quark. Recent measurements from the Large Hadron Collider have refined our knowledge of these parameters, but significant uncertainties remain. The measured mass of the Higgs boson, approximately 125 billion electron volts, is tantalizingly close to the boundary between a stable and metastable vacuum, but the uncertainties in the measurement and the theoretical calculations are still large enough that we cannot definitively determine which case applies. If the standard model of particle physics is complete and no new physics exists beyond what we've already discovered, then most calculations suggest that our vacuum is indeed metastable. However, the discovery of new particles or interactions at higher energies could completely change this conclusion. The stability of our vacuum depends on the detailed structure of physics at energy scales that we have not yet fully explored. Even if our vacuum is metastable, the timescale for decay remains highly uncertain. Most estimates suggest that the average lifetime of a metastable vacuum would be enormously long, potentially 10 to the 100 years or more. This is so much longer than the current age of the universe, about 14 billion years, that vacuum decay would be virtually impossible over any conceivable timescale. However, these calculations assume that vacuum decay occurs only through random quantum fluctuations. High-energy astrophysical events, like black hole formation or cosmic ray interactions, might provide the energy needed to trigger decay more rapidly. Even so, the fact that such events have been occurring throughout cosmic history without triggering vacuum decay suggests that our vacuum is reasonably stable. The predictions of accelerating cosmic expansion that could lead to a big rip scenario are based on much more solid observational foundations. The discovery that cosmic expansion is accelerating, recognized with the 2011 Nobel Prize in Physics, is one of the most significant cosmological findings of the past century. Multiple independent observations, including supernova surveys, cosmic microwave background measurements, and large-scale structure studies, all confirm that expansion is indeed accelerating. However, the nature of the dark energy driving this acceleration remains completely mysterious. We know that it currently accounts for about 68% of the total energy density of the universe. And we know that it causes expansion to accelerate rather than decelerate. But we have no direct knowledge of what dark energy actually is or how its properties might evolve over time. If dark energy is truly constant, as suggested by the simplest models, then cosmic expansion will continue to accelerate gradually. But no catastrophic changes are expected. The universe will eventually become cold and empty as galaxies drift apart. But this process will take many tens of billions of years, and the fundamental laws of physics will remain unchanged. However, if dark energy is dynamic and evolving, as suggested by more complex models called quintessence, then its properties could change over time. Some quintessence models do predict that dark energy could evolve toward configurations that would tear apart the fabric of space-time itself, leading to a big rip scenario. The observational constraints on such evolution are still relatively weak. Current supernova surveys and other distance measurements can detect only relatively large changes in dark energy properties over cosmic time. More subtle evolution that could eventually lead to catastrophic changes might not be detectable with current techniques. Future observations, including more extensive supernova surveys and more precise measurements of cosmic expansion, will provide much tighter constraints on dark energy evolution. The Large Synoptic Survey Telescope and other next-generation facilities will observe millions of supernovas and other distance indicators, potentially detecting changes in dark energy properties that are currently unobservable. The predictions of proton decay from grand unified theories occupy a middle ground between solid theoretical motivation and observational confirmation. The theoretical arguments for grand unification are compelling, successfully explaining several puzzling features of the Standard Model, including the apparent unification of coupling constants at high energies. However, the predicted proton lifetimes are so long that they are extremely difficult to measure directly. The most sensitive experiments, involving thousands of tons of ultra-pure water monitored for years at a time, have searched for proton decay events without finding any. These null results have pushed the lower limit on the proton lifetime to over 10 to the 34 years, longer than most grand unified theories originally predicted. The absence of observed proton decay doesn't rule out grand unification, but it does suggest that if protons do decay, the timescale is even longer than initially expected. Even if protons eventually decay with lifetimes of 10 to the 36 years or more, this would have no practical consequences for the foreseeable future, though it would eventually lead to the dissolution of all atomic matter over unimaginably long timescales. The exotic possibilities suggested by string theory and other attempts to unify quantum mechanics with general relativity remain largely untested by observation. String theory makes many specific predictions about the behavior of matter and energy at extremely high energies. But most of these predictions involve energy scales far beyond what we can currently probe experimentally. Some aspects of string theory, such as the prediction of extraspatial dimensions, could potentially be tested by future experiments. The Large Hadron Collider and its planned upgrades might detect signatures of extra dimensions if they exist at accessible energy scales. However, most string theory predictions involve energies comparable to the Planck scale, about 10 to the 19 billion electron volts, which is far beyond any conceivable experimental reach. The holographic principle and other exotic ideas about the fundamental nature of space-time are similarly difficult to test directly. These concepts arise naturally from attempts to reconcile quantum mechanics with general relativity, and they may be essential for understanding phenomena like black hole evaporation and the early universe. However, their implications for the long-term stability of physical laws remain highly speculative. Given this mixed scientific status, how should we assess the overall likelihood that the laws of physics are temporary? The answer depends on what specific type of change we're considering and over what timescale. For gradual changes in fundamental constants over cosmic timescales, the observational evidence is suggestive but not conclusive. The theoretical frameworks that predict such changes are plausible but largely untested. If such changes are occurring, they appear to be slow enough that they would have no practical consequences over human timescales, though they could be scientifically significant for understanding the fundamental nature of physical law. For sudden, catastrophic changes like vacuum decay or cosmological phase transitions, the theoretical possibility is well established, but the likelihood and timescale remain highly uncertain. Most estimates suggest that such events, if they occur at all, would happen over timescales so long that they pose no immediate threat. However, the uncertainties in these estimates are large enough that we cannot completely rule out more rapid changes. The accelerating expansion of the universe is definitely occurring, but whether it will evolve into something more dramatic, like a big rip, depends on the unknown properties of dark energy. Current observations favor models where dark energy is constant or evolving slowly, but more exotic behavior remains possible. Perhaps the most honest assessment is that we are living through a remarkable period in the history of science, when our understanding of fundamental physics is advancing rapidly but remains incomplete in crucial areas. We have discovered that the universe is far stranger and more dynamic than previous generations imagined, but we are still working to understand the full implications of these discoveries. The possibility that physical laws are temporary represents a natural extension of what we've already learned about cosmic evolution. Just as we've discovered that the universe itself has a history, with galaxies, stars, and planets forming and evolving over cosmic time, we're beginning to appreciate that the laws governing these processes might also have their own evolutionary history. Whether this evolution continues into the future and what form it might take remains an open question. The scientific evidence suggests that dramatic changes are possible but not certain, and that any such changes would likely occur over timescales much longer than human civilization has existed. This conclusion might seem unsatisfying, but it reflects the genuine state of scientific knowledge at the frontiers of our understanding. We are probing questions about the ultimate nature of reality that push the boundaries of both theoretical physics and observational capability. The answers we're seeking involve energies, distances, and timescales that challenge our ability to gather direct evidence. What we can say with confidence is that the question of temporary physical laws is not merely philosophical speculation, but represents a legitimate area of scientific inquiry. The theoretical frameworks exist, the observational techniques are being developed, and the experimental searches are ongoing. Whether the laws of physics are truly eternal or merely temporary may be one of the most profound questions that science can address. The implications of the answer, whichever way it goes, will reshape our understanding of our place in the cosmos and the ultimate fate of everything that exists. In the meantime, the very fact that we can seriously consider such questions represents a remarkable achievement of human curiosity and scientific capability. If true, what does temporary physics mean for science and humanity? If the laws of physics are indeed temporary, subject to change over cosmic time, the implications for both science and human civilization would be so profound that they would fundamentally transform how we understand our place in the universe and how we approach the future. Let's explore what this brave new world of changeable physics would mean for the scientific enterprise, human society, and our species' long-term survival. For science itself, the confirmation that physical laws are temporary would represent both a crisis and an opportunity of unprecedented magnitude. The crisis would stem from the collapse of one of science's most fundamental assumptions, that the laws of nature are universal and eternal. This principle of uniformity has been the bedrock of scientific reasoning since the scientific revolution. It's what allows us to apply knowledge gained in laboratories on Earth to understand distant stars and galaxies, to use fossil evidence to reconstruct ancient climates, and to make predictions about future phenomena based on past observations. If physical laws can change, then this entire edifice of scientific reasoning becomes provisional and uncertain. Every scientific theory, from quantum mechanics to general relativity to evolutionary biology, would need to be reinterpreted as descriptions of temporary local conditions rather than eternal, universal truths. The laws of thermodynamics, conservation of energy, and even basic mathematical relationships, like the inverse square law of gravitation, would become contingent facts about our current cosmic epoch rather than absolute principles. This transformation would force scientists to develop entirely new methodologies for studying a universe where the rules themselves evolve. Instead of seeking timeless mathematical laws, science would become more like meteorology or ecology, fields that study complex dynamic systems where patterns emerge and dissolve over time. We would need new theoretical frameworks for understanding how physical laws evolve, what drives their changes, and how to predict future transformations. The opportunity, however, would be equally extraordinary. Science would gain access to entirely new realms of phenomena and possibilities. If physical laws can change, then we might eventually understand the mechanisms behind these changes, and perhaps even learn to influence them. The prospect of participating in the evolution of physical law itself represents the ultimate frontier for scientific exploration. We might discover that consciousness plays a fundamental role in determining physical law, opening up new connections between physics and neuroscience, psychology, and philosophy of mind. We might find that the universe is far more creative and open-ended than we ever imagined, with genuine novelty emerging at the most fundamental levels of reality. The implications for technology would be even more dramatic and immediate. Our entire technological civilization is built on the assumption that physical laws remain constant. Every machine, from simple mechanical devices to complex computer systems, relies on consistent behavior of materials, forces, and energy relationships. If these could change, then all of our technology would become potentially obsolete. Consider the implications for space exploration. We launch spacecraft based on precise calculations of orbital mechanics, assuming that gravitational forces will remain constant throughout the mission. If the gravitational constant were to drift over time, missions to distant planets or other star systems could fail catastrophically as their trajectories deviate from predicted paths. More fundamentally, if the fine structure constant were to change, altering the strength of electromagnetic interactions, then all of our electronic technology would be affected. Computer processors, which depend on precise control of electron behavior in semiconductor materials, might stop functioning correctly. Power grids, communication systems, and countless other technologies that rely on electromagnetic phenomena would need to be continuously redesigned and updated. This would create an urgent need for what we might call adaptive technology, systems designed to function despite changing physical laws. Instead of building devices based on fixed specifications, engineers would need to develop technologies that can automatically adjust their operation as fundamental constants drift or as phase transitions alter the basic rules of physics. Such adaptive systems would require sophisticated, real-time monitoring of fundamental constants and physical laws, along with the ability to rapidly reconfigure hardware and software in response to detected changes. This represents a completely new paradigm for technological development, one that prioritizes flexibility and adaptability over efficiency and optimization. The economic implications would be staggering. The entire concept of long-term investment would need to be reconsidered if the physical foundations of economic activity could change without warning. How do you calculate the return on investment for a power plant if the nuclear or chemical reactions that power it might behave differently in the future? How do you design insurance policies for a world where the basic physics underlying risk assessment could evolve? Financial markets, which are already complex systems sensitive to countless variables, would face an entirely new category of fundamental uncertainty. The possibility of changing physical laws would create a form of systemic risk that dwarfs anything currently considered in economic modeling. Investors would need to factor in the possibility that entire categories of assets could become worthless if the physical laws supporting them were to change. This might lead to a shift toward more flexible, short-term economic strategies and away from the kind of long-term planning that characterizes modern industrial civilization. Alternatively, it might drive the development of new forms of economic organization better adapted to fundamental uncertainty, perhaps resembling the resilient, adaptive strategies employed by biological ecosystems. For human society more broadly, the knowledge that physical laws are temporary would likely trigger profound psychological and cultural responses. The realization that reality itself is contingent and changeable would challenge some of humanity's deepest assumptions about the nature of existence and our place in the cosmos. Some people might respond with despair or nihilism, concluding that nothing really matters if the very foundations of existence are temporary. If atoms, molecules, and even the forces that hold them together could disappear or be transformed beyond recognition, then human life, civilization, and all of our achievements might seem utterly insignificant. Others might find the idea liberating and inspiring. If reality is genuinely open-ended and creative, then human consciousness might play a more significant role in shaping the cosmos than we ever imagined. Instead of being passive observers of a predetermined universe, we might be active participants in an ongoing cosmic improvisation. Religious and spiritual communities would face particularly complex challenges in integrating the concept of temporary physical laws with their existing beliefs. Traditional concepts of eternal divine law or unchanging spiritual principles would need to be reconciled with a universe where even the most basic physical constants are subject to change. Some religious traditions might embrace the idea as evidence of divine creativity and ongoing creation, seeing changing physical laws as manifestations of a dynamic, living universe continuously renewed by divine action. Others might view it as threatening to concepts of cosmic order and purpose, requiring significant theological adaptation. The implications for education would be profound. If physical laws are temporary, then science education would need to emphasize the provisional and evolving nature of scientific knowledge even more than it currently does. Students would need to learn not just current scientific theories, but also how to think about knowledge that might become obsolete due to changes in the physical world itself. This might actually improve scientific education by emphasizing the dynamic, creative nature of scientific inquiry, rather than presenting science as a collection of fixed facts to be memorized. Students would need to develop stronger critical thinking skills and greater comfort with uncertainty and change. For human survival and the long-term future of our species, temporary physical laws would create both existential threats and unprecedented opportunities. On the threat side, any significant change in fundamental constants or physical laws could make Earth uninhabitable or even destroy all matter as we know it. This would create an urgent imperative for developing what we might call cosmic resilience, the ability to survive and thrive despite changes in fundamental physics. This might require developing space-based civilizations that could potentially survive regional changes in physical law, or even learning to exist in forms that don't depend on current atomic and molecular structures. The ultimate goal might be to evolve beyond dependence on any particular set of physical laws, developing forms of organization and consciousness that could persist through cosmic phase transitions. This represents a new kind of evolutionary challenge, one that goes beyond biological adaptation to encompass adaptation to changing physics itself. On the opportunity side, if we could understand and potentially influence the evolution of physical laws, we might gain access to capabilities that seem impossible under current physics. We might learn to create new forms of matter and energy, to manipulate space and time in novel ways, or even to participate directly in the creation of new physical realities. This could represent the ultimate expression of human creativity and intelligence, moving beyond merely using the laws of physics to actually participating in their creation and evolution. Such capabilities would make us truly cosmic citizens, no longer limited to a single planet or even a single configuration of physical law. The scientific research priorities would shift dramatically toward understanding the mechanisms behind changing physical laws. This would require major investments in theoretical physics, cosmology, and the development of new observational techniques capable of detecting subtle changes in fundamental constants or early signs of impending phase transitions. We would need global monitoring systems capable of detecting changes in physical laws anywhere in the observable universe, along with rapid response capabilities for dealing with approaching regions of altered physics. This might require unprecedented levels of international cooperation and coordination, as the threat of changing physics would affect all of humanity equally. The development of technologies for surviving or adapting to changing physics would become a critical priority. This might include research into exotic forms of matter and energy that could remain stable through phase transitions, or the development of artificial intelligences capable of rapidly redesigning technology in response to changing physical laws. Perhaps most importantly, we would need to develop new frameworks for meaning and purpose that could withstand the knowledge that physical reality itself is temporary. Human culture, ethics, and spirituality would need to evolve to embrace fundamental uncertainty while still providing the stability and direction necessary for individual and collective flourishing. This might lead to new forms of wisdom that emphasize process over product, becoming over being, and creativity over preservation. Instead of seeking to build permanent monuments or lasting legacies, human culture might shift toward embracing the creative process itself as the highest expression of consciousness and meaning. The relationship between individual and collective human identity would also need to evolve. If physical laws can change, then the boundary between self and cosmos becomes more fluid and dynamic. Individual survival might become less important than the survival and evolution of consciousness itself, leading to new forms of collective identity and purpose. In education, research, and cultural development, we would need to cultivate qualities like adaptability, creativity, and comfort with uncertainty. The rigid, specialized knowledge that characterizes much of current education would need to be supplemented with more flexible, integrative approaches that prepare people to thrive in a world of fundamental change. Perhaps the most profound implication is that temporary physical laws would force humanity to mature as a species in ways we can barely imagine. We would need to move beyond parochial concerns and tribal conflicts to embrace our role as conscious participants in cosmic evolution. The knowledge that reality itself is at stake would provide a perspective that makes petty human conflicts seem absurdly small. This could catalyze the emergence of a truly planetary and eventually cosmic civilization united not by common genetics or culture, but by shared participation in the ongoing creation of reality. The temporary nature of physical laws, rather than making existence meaningless, might reveal it to be the most meaningful thing imaginable. A creative collaboration between consciousness and cosmos in the ongoing invention of what it means to exist. In this context, every human life, every moment of consciousness, every creative act becomes infinitely precious, not because it will last forever, but because it contributes to the evolving cosmos of which we are an integral part. The end of eternal physical laws might paradoxically reveal the beginning of eternal creativity, with consciousness itself as the thread that connects one phase of cosmic evolution to the next. Yet could such impermanence explain mysteries we currently face in physics? One of the most intriguing aspects of temporary physical laws is their potential to solve some of the deepest mysteries that have puzzled physicists for decades. If the laws of physics can change over time, then many phenomena that seem impossible or inexplicable under our current understanding might actually be evidence of physics in transition, remnants of previous cosmic epochs, or harbingers of changes yet to come. Perhaps the most famous mystery that temporary laws might help explain is the fine-tuning problem. This refers to the remarkable fact that the fundamental constants of nature seem to be precisely calibrated to allow for the existence of complex structures like atoms, stars, planets, and ultimately life itself. Change any of these constants by even a tiny amount, and the universe becomes a sterile wasteland incapable of supporting any form of complexity. For example, if the strong nuclear force were just 5% weaker, deuterium nuclei would be unstable, preventing the formation of heavy elements in stars. If it were 5% stronger, protons would bind together so efficiently that hydrogen would be rare, eliminating the fuel that powers main sequence stars for billions of years. The electromagnetic force, the weak nuclear force, and gravity all seem to have similarly fine-tuned values. The traditional response to this puzzle has been to invoke either intelligent design or the anthropic principle. The design argument suggests that some intelligence deliberately chose these values to make complexity possible. The anthropic principle argues that we observe fine-tuned constants simply because we exist. In universes with different constants, there would be no observers to notice the difference. But temporary physical laws offer a third possibility. What if the constants aren't permanently fine-tuned, but are temporarily passing through values that happen to allow complexity to emerge? In this view, the universe spends most of its time in phases where the constants take values that make complexity impossible. But occasionally, through the natural evolution of physical law, the constants drift into ranges where atoms can form, stars can shine, and life can emerge. This would mean we're living during a special but temporary window of cosmic history when the physical laws happen to support complex structures. Eventually, the constants will drift away from their current values, making our kind of complexity impossible, but potentially enabling entirely different forms of organization that we can't currently imagine. This temporal fine-tuning hypothesis has several advantages over traditional explanations. Unlike intelligent design, it doesn't require invoking any external agent or purpose. Unlike the anthropic principle, it doesn't require assuming the existence of vast numbers of parallel universes with different constants. Instead, it suggests that our own universe naturally explores different regions of the space of possible physical laws over cosmic time. The dark energy mystery provides another example where temporary laws might offer new insights. Dark energy, which makes up about 68% of the universe's total energy density, is causing cosmic expansion to accelerate rather than decelerate. This is completely unexpected based on our understanding of matter and energy, which should gravitationally attract and slow down expansion. The most straightforward explanation for dark energy is Einstein's cosmological constant, a form of energy inherent in space itself. But when physicists try to calculate what this constant should be based on quantum field theory, they get an answer that's larger than the observed value by a factor of 10 to the 120, possibly the worst prediction in the history of science. This enormous discrepancy suggests that our understanding of vacuum energy and the cosmological constant is fundamentally flawed. But what if the cosmological constant isn't actually constant? What if it's a dynamical field that evolves over cosmic time, and we happen to be observing it during a period when it has a small but non-zero value? Some models of evolving dark energy, called quintessence models, predict exactly this behavior. The dark energy field starts with a large value in the early universe, gradually decreases over cosmic time, and might eventually approach zero or even become negative. This evolution could explain why the current value is so much smaller than naive theoretical predictions. We're simply observing it at a time when it has evolved to a relatively small but still significant value. If dark energy is indeed evolving, this could have profound implications for the future of the universe. Instead of eternal acceleration leading to a cold, empty cosmos, the evolution of dark energy might lead to new phases of cosmic history with completely different expansion behavior. The universe might even eventually begin contracting again, leading to a big crunch that could trigger a new cycle of cosmic evolution. The hierarchy problem in particle physics presents another puzzle that temporary laws might help resolve. This problem concerns the enormous difference in strength between gravity and the other fundamental forces. Gravity is about 10 to the 39 times weaker than electromagnetism, a disparity so large that it seems to require an explanation. Why is gravity so much weaker than the other forces? In theories with extra dimensions, this weakness could be explained if gravity, unlike the other forces, can spread out into additional spatial dimensions that we don't directly perceive. But this raises the question of why the extra dimensions have their current size, and why gravity is confined to behave the way it does in our three-dimensional experience. If the fundamental structure of space-time can evolve over cosmic time, then the hierarchy problem might be a temporary feature of our current cosmic epoch. Perhaps gravity was much stronger in the early universe, when the extra dimensions were a different size or had a different configuration. The current weakness of gravity might reflect the particular way that space-time has evolved since the Big Bang. This could mean that gravity will eventually become stronger again as space-time continues to evolve, potentially leading to a future universe where gravitational effects dominate over electromagnetic and nuclear forces. Such a change would completely transform the physics of matter and energy, creating possibilities for new forms of structure and organization that are impossible under current conditions. The quantum measurement problem represents one of the most fundamental puzzles in physics, and temporary laws might offer new approaches to understanding it. Quantum mechanics describes particles as existing in superpositions of different states until they are measured, at which point the superposition collapses to a single definite state. But what exactly constitutes a measurement, and why does measurement have this special effect? Traditional interpretations of quantum mechanics either accept the collapse as a fundamental feature of reality or invoke parallel universes where all possible measurement outcomes occur simultaneously. But what if the apparent collapse of quantum superpositions is actually evidence of evolving physical law? Perhaps the boundary between the quantum and classical worlds is not fixed, but changes over cosmic time. In the early universe, when energy densities were enormous, quantum effects might have dominated even at macroscopic scales. As the universe cooled and expanded, the transition from quantum to classical behavior might have gradually shifted to smaller and smaller scales. If this transition continues to evolve, we might eventually find ourselves in a universe where quantum effects become apparent at larger scales again, or conversely, where quantum behavior is suppressed even at currently quantum scales. The measurement problem might thus be a temporary feature of our current cosmic epoch, rather than a permanent aspect of reality. The matter-antimatter asymmetry presents another mystery that temporary laws might illuminate. The early universe should have contained equal amounts of matter and antimatter, which would have completely annihilated each other, leaving a universe of pure radiation. The fact that matter dominates over antimatter in the current universe requires some process that violates the symmetry between matter and antimatter. Current theories explain this asymmetry through processes that occurred during the early cosmic phase transitions, when the fundamental forces were separating and physical laws were rapidly changing. But what if similar symmetry breaking processes could occur again in the future? If physical laws continue to evolve, we might witness new forms of symmetry breaking that could create entirely new categories of matter and energy. The current dominance of ordinary matter over antimatter might be just one phase in a longer cosmic story that includes periods dominated by different forms of matter, or even exotic states that don't fit current categories. The cosmic coincidence problem provides yet another example. Dark energy and dark matter currently have comparable energy densities, even though they evolve very differently as the universe expands. Dark matter density decreases as the universe grows, while dark energy density appears to remain constant. The fact that we observe them at a time when their densities are similar seems like an incredible coincidence. But if both dark energy and dark matter are aspects of evolving physical fields, then this coincidence might reflect a deeper connection between these phenomena. Perhaps they represent different aspects of the same underlying field that governs the evolution of physical law itself. Their current comparable densities might indicate that we're living during a special transition period in the evolution of cosmic physics. The black hole information paradox offers another area where temporary laws might provide new insights. When matter falls into a black hole, quantum mechanics says that the information describing that matter must be preserved. But general relativity suggests that this information is destroyed when the black hole eventually evaporates through Hawking radiation. If the laws governing black hole physics can evolve over time, then this paradox might be resolved by recognizing that different phases of cosmic evolution have different rules for information processing and storage. What appears to be information destruction under current physical laws might actually be information transformation into forms that will become accessible when the laws of physics evolve into new configurations. The origin of cosmic inflation, the period of exponential expansion in the very early universe, remains mysterious. What caused inflation to begin, and what caused it to end? Why did it produce exactly the right conditions for the formation of galaxies and large-scale structure? If inflation was itself a manifestation of evolving physical law, then these questions might have simpler answers. Inflation might represent a natural phase in the evolution of space-time itself, triggered by the same processes that separated the fundamental forces and established the current configuration of physical law. The fine-tuned nature of inflation, which seems to require very specific initial conditions and field properties, might reflect the fact that we're observing the universe during a period when the evolution of physical law happened to produce conditions suitable for structure formation. Other phases of this evolution might produce very different cosmological behavior. The vacuum catastrophe, where quantum field theory predicts a vacuum energy density that's enormously larger than observed, might also be explained by evolving physical laws. If the vacuum state itself evolves over cosmic time, then the current energy density might represent a temporary minimum in a longer evolutionary process. This could mean that the vacuum energy will eventually increase again, driving new periods of cosmic inflation or other exotic behavior. The current universe, with its relatively stable vacuum and slowly accelerating expansion, might represent a brief interlude between more dramatic phases of cosmic evolution. Perhaps most intriguingly, the apparent fine-tuning of physical laws to permit the emergence of consciousness might reflect a deep connection between mind and the evolution of physical law. If consciousness plays a role in determining or selecting physical laws, then the fact that we observe laws compatible with consciousness might not be a coincidence, but a consequence of the participatory nature of cosmic evolution. This would suggest that the mysteries of physics are not separate problems to be solved independently, but different aspects of a single, deeper mystery. The relationship between consciousness, and the evolution of physical reality. The temporary nature of physical laws might be intimately connected to the emergence and evolution of conscious observers. In this view, physics doesn't just describe the behavior of unconscious matter and energy, but the co-evolution of matter, energy, and consciousness within an open-ended cosmic process. The mysteries we observe might be symptoms of a universe still in the process of creating itself, with consciousness as both observer and participant in that creation. The resolution of these mysteries through temporary physical laws would represent a fundamental shift in how we understand the relationship between physics and consciousness, between the observer and the observed, between the temporary and the eternal. Instead of seeking final answers to these puzzles, we might need to learn to appreciate them as aspects of an ongoing cosmic conversation between mind and reality. So what can we safely and conclusively summarize scientifically? After exploring the theoretical possibilities, observational evidence, and profound implications of temporary physical laws, we must now step back and ask, what can we definitively conclude from our current scientific understanding? What aspects of this investigation rest on solid empirical foundations, and what remains speculative? The answers to these questions will determine how seriously we should take the possibility that the laws of physics themselves have an expiration date. Let's begin with what we know beyond any reasonable doubt. The laws of physics have changed before and changed dramatically. This is not speculation or theoretical possibility, but established scientific fact, supported by multiple independent lines of evidence that have been confirmed by decades of observations and experiments. The early universe underwent a series of phase transitions that fundamentally altered how physics worked. In the first fraction of a second after the Big Bang, the four fundamental forces that govern our current universe were unified into a single superforce. As the universe expanded and cooled, this unity was broken through spontaneous symmetry, breaking processes that separated gravity, electromagnetism, and the strong and weak nuclear forces into the distinct interactions we observe today. These phase transitions didn't just change the relative strengths of different forces, they completely rewrote the rules governing how matter and energy interact. Before electroweak symmetry breaking, photons didn't exist in their current form. Before the separation of the strong force, quarks couldn't bind together to form protons and neutrons. The very categories of particles and interactions that define our current physical reality emerged from these early transitions. This historical precedent is crucial because it proves that the assumption of unchanging physical laws, which has been central to scientific thinking since Newton, is demonstrably false when applied to cosmic history. The universe has already undergone the kind of fundamental transformations in physical law that we're considering for the future. We also know with certainty that the current state of the universe is temporary. Cosmic expansion is accelerating, driven by the mysterious dark energy that makes up about 68% of the universe's total energy content. This acceleration is carrying galaxies away from each other at ever-increasing speeds, gradually dissolving the large-scale structure that has characterized the universe for billions of years. Even if no further changes occur in the fundamental laws of physics, the current cosmic epoch will eventually end. In about 5 billion years, the Sun will exhaust its nuclear fuel and begin its transformation into a red giant, making Earth uninhabitable. On much longer timescales, stellar formation will cease as the universe expands and cools, leaving behind a cold cosmos of slowly cooling stellar remnants. These changes represent the evolution of cosmic structure rather than changes in fundamental physical law, but they demonstrate that the universe is a dynamic, evolving system rather than a static, eternal configuration. Nothing about the current state of reality is guaranteed to persist forever. The evidence for more dramatic changes in physical law is less definitive, but still scientifically significant. multiple research groups have reported possible variations in fundamental constants, like the fine structure constant over cosmic time, based on observations of distant quasar light. While these results remain controversial and disputed, they represent genuine scientific measurements using sophisticated observational techniques. The claimed variations are extraordinarily small, only a few parts per million over billions of years, but they would be scientifically revolutionary if confirmed. They suggest that what we call fundamental constants might actually be slowly evolving fields that change over cosmic timescales. The theoretical frameworks that predict such changes, including string theory and various models of evolving scalar fields, are mathematically sophisticated and address real problems in fundamental physics. While these theories remain largely untested by direct experiment, they arise naturally from attempts to unify quantum mechanics with general relativity and to understand the deep structure of spacetime. The calculations regarding vacuum stability represent perhaps the most concrete application of established physics to the question of changing physical laws. These calculations use the well-tested standard model of particle physics, combined with precise measurements of particle masses and coupling constants from experiments like those at the Large Hadron Collider. The results suggest that our current vacuum state might be metastable rather than absolutely stable. If true, this would mean that the universe could undergo a catastrophic phase transition to a lower energy vacuum state, completely rewriting the laws of physics in the process. However, the timescales involved appear to be enormously long, much longer than the current age of the universe. What makes these calculations particularly noteworthy is that they're based on well-established physics rather than speculative new theories. The possibility of vacuum instability emerges naturally from applying known physical principles to the measured properties of fundamental particles. The observational evidence for accelerating cosmic expansion provides another solid foundation for considering how physical laws might evolve. The acceleration is definitely occurring, confirmed by multiple independent observations, including supernova surveys, cosmic microwave background measurements, and studies of large-scale structure. However, the nature of the dark energy driving this acceleration remains completely mysterious. If dark energy is truly constant, as assumed in the simplest models, then cosmic expansion will continue to accelerate gradually without any sudden changes in physical law. But if dark energy is dynamic and evolving, as suggested by more complex quintessence models, then its future evolution could potentially trigger new phase transitions. The theoretical possibility of more exotic scenarios, such as the Big Rip, where accelerating expansion eventually tears apart the fabric of spacetime itself, represents legitimate scientific speculation based on known physics. While these scenarios are not currently favored by observations, they remain within the realm of possibility, given our incomplete understanding of dark energy. When we combine all of this evidence, a clear scientific conclusion emerges. The permanence of physical laws is an assumption, not an established fact. This assumption has served science well for centuries, enabling remarkable progress in understanding and predicting natural phenomena. But it is not required by the evidence, and there are good reasons to question its universal validity. The historical evidence shows that physical laws have changed before. The observational evidence suggests they might be changing now, albeit very slowly. The theoretical evidence indicates they could change again in the future through processes ranging from gradual constant evolution to sudden vacuum decay or cosmological phase transitions. This doesn't mean that dramatic changes in physical law are imminent or even likely on human timescales. Most theoretical estimates suggest that any such changes would occur over periods much longer than the current age of the universe. But the mere possibility that they could occur represents a fundamental shift in how we understand the nature of physical reality. Perhaps most importantly, the investigation of temporary physical laws has revealed the provisional nature of all scientific knowledge. Every scientific theory, no matter how well tested or widely accepted, represents our best current understanding of phenomena that might themselves be evolving. The laws of thermodynamics, quantum mechanics, general relativity, and even basic conservation principles might all be approximations that apply only within certain ranges of cosmic conditions. This doesn't make science less valuable or reliable. Within the domains where they apply, scientific theories remain extraordinarily successful at describing and predicting natural phenomena. But it does make science more humble and open-ended, always subject to revision in light of new evidence or changing cosmic conditions. The scientific method itself emerges strengthened from this investigation. The willingness to question even the most fundamental assumptions, to follow evidence wherever it leads, and to consider possibilities that challenge conventional wisdom, demonstrates the power and flexibility of scientific thinking. Science's greatest strength lies not in providing final answers, but in its capacity for self-correction and continuous refinement. From a practical standpoint, the possibility of temporary physical laws doesn't require any immediate changes in how we conduct science or technology. The timescales involved in most scenarios are so long that they would have no practical consequences for human civilization as it currently exists. We can continue to build bridges, design computers, and launch spacecraft with confidence that the physical laws we rely on will remain stable for the foreseeable future. But from a philosophical and long-term perspective, the implications are profound. If physical laws are indeed temporary, then we are living during a particular phase of cosmic evolution, one that happens to support the complex structures and processes that make life and consciousness possible. This phase will eventually end, to be replaced by other phases with different possibilities and constraints. This realization transforms our understanding of humanity's place in the cosmos. We are not just observers of a fixed, eternal universe, but participants in an ongoing cosmic drama, where the very rules of existence are subject to change. Our presence as conscious observers might not be an accident, but an integral part of how the universe evolves and transforms itself. The ultimate scientific takeaway is that reality is far more dynamic and open-ended than previous generations imagined. The universe is not a clockwork mechanism operating according to eternal laws, but a creative, evolving system where genuine novelty can emerge at the most fundamental levels. Whether physical laws will actually change in the future remains an open question. The scientific evidence suggests it's possible but not certain, likely but not imminent. What we can say with confidence is that the question itself represents one of the most profound challenges in contemporary science, one that pushes the boundaries of both theoretical understanding and observational capability. The search for answers will require new levels of precision in measuring fundamental constants, new theoretical frameworks for understanding cosmic evolution, and new observational techniques for detecting subtle changes in physical law. It will also require new forms of international cooperation and long-term thinking, as the phenomena we're studying operate on scales that transcend national boundaries and human lifetimes. Perhaps most importantly, it will require a new kind of scientific courage, the willingness to question everything we think we know about the nature of reality and to follow the evidence wherever it leads, even if it challenges our most basic assumptions about existence itself. The current state of physics, with its elegant theories and precise predictions, likely represents a temporary equilibrium in the ongoing evolution of cosmic law. We are privileged to live during a period when the universe has achieved sufficient stability and complexity to support conscious observers capable of contemplating these deep questions. But this period, like all others in cosmic history, will eventually pass. The laws that govern our current reality will give way to new configurations, new possibilities, and new challenges. Whether humanity will be present to witness these future transformations, and whether we will play a role in shaping them, remains to be determined. What we can say with scientific confidence is that we inhabit a universe where change is the only constant, where even the laws of physics themselves participate in the grand evolutionary story that connects the Big Bang to whatever cosmic future awaits. In such a universe, every moment of stability is precious, every instance of complexity is remarkable, and every conscious thought is a temporary victory against the vast forces of cosmic change. Living in such a universe requires both humility about our ultimate knowledge and wonder at our extraordinary privilege in being able to contemplate these questions at all. The laws of physics may indeed be temporary, but the human capacity to understand and marvel at this possibility represents one of the most remarkable achievements in the entire history of cosmic evolution. We began this journey with a simple but profound question. What if the laws of physics are not eternal truths, but temporary rules that could change or even disappear entirely? After exploring the scientific evidence, theoretical possibilities, and philosophical implications, we arrive at a conclusion that is both humbling and awe-inspiring. The universe we inhabit is far stranger and more dynamic than our ancestors ever imagined. The solid, reliable reality that seems so permanent and unchanging is actually a temporary arrangement of matter, energy, space, and time that emerged from cosmic processes we're only beginning to understand and will eventually give way to configurations we cannot yet imagine. The laws of physics that govern every atom in our bodies, every chemical reaction in our cells, every photon of light that enables us to see, and every gravitational force that keeps our planet in orbit around the sun are not eternal commandments carved into the fabric of reality. They are provisional guidelines that arose from the cooling and expansion of the early universe and could potentially be rewritten by future cosmic events. This realization transforms everything about how we understand our place in the cosmos. We are not residents of a permanent cosmic home, but temporary guests in a universe that is still creating itself. The physical laws that make our existence possible represent a brief window of cosmic stability between periods of fundamental change. Every breath we take, every thought we think, every moment of consciousness exists within this fragile window. The electromagnetic forces that allow neurons to fire in our brains, the strong nuclear forces that hold together the carbon atoms in our DNA, the gravitational forces that keep our atmosphere from drifting into space, all of these operate according to rules that emerged from cosmic evolution and could someday be transformed beyond recognition. Yet rather than making existence seem meaningless or insignificant, this realization reveals it to be extraordinarily precious. In a universe where even the most fundamental laws of nature are temporary, the emergence of complexity, life, and consciousness becomes not just remarkable, but almost miraculous. We exist during a cosmic moment when the laws of physics happen to permit the intricate dance of particles and forces that create stars, planets, molecules, cells, and thinking beings. The scientific evidence we've examined shows that this is not merely philosophical speculation, but a legitimate area of scientific inquiry. The laws of physics have definitely changed before, during the phase transitions that shaped the early universe. They might be changing now, as suggested by observations of possibly varying fundamental constants. And they could change again in the future, through processes ranging from gradual evolution to sudden cosmic catastrophe. The timescales involved are typically much longer than human civilization has existed, longer than our species has walked the Earth, longer than life has existed on our planet. Most scenarios for changing physical laws operate over billions or trillions of years, making them irrelevant for practical human concerns. But the mere possibility that they could occur forces us to confront the ultimate contingency of existence. If the laws of physics have an expiration date, then everything we consider real and permanent exists within that expiration period. Atoms, molecules, chemistry, biology, consciousness, and civilization all depend on the particular configuration of physical law that happens to prevail in our cosmic epoch. Outside that configuration, these phenomena might be impossible or might take forms so alien that we cannot currently comprehend them. But this perspective also opens up extraordinary possibilities. If physical laws can change, then the universe is far more creative and open-ended than we previously imagined. Instead of being locked into a single set of rules for all eternity, reality might be capable of genuine innovation at the most fundamental level. New forms of matter and energy might emerge that have no counterpart in current physics. New types of forces might arise that create possibilities for organization and complexity that we cannot currently envision. New relationships between space, time, matter, and consciousness might develop that transform the very meaning of existence. Perhaps most intriguingly, consciousness itself might play a role in this cosmic creativity. If the act of observation influences physical reality, as some interpretations of quantum mechanics suggest, then conscious beings might participate in the evolution of the very laws that govern their existence. We might be not just products of cosmic evolution, but active participants in its continuation. This possibility transforms science from a passive enterprise of discovering pre-existing truths into an active collaboration between consciousness and cosmos in the ongoing creation of reality. Every scientific experiment, every theoretical insight, every moment of understanding might contribute to the universe's evolving self-knowledge and self-transformation. The implications extend far beyond academic physics. If reality is genuinely open-ended and creative, then human potential might be far greater than we currently imagine. The boundaries that seem to limit what we can achieve might be artifacts of our current cosmic epoch rather than absolute constraints on possibility. Future phases of cosmic evolution might permit forms of existence and experience that are currently impossible. We might someday transcend the limitations of biological bodies, chemical brains, and planetary environments, not through technological advancement alone, but through participation in the fundamental transformation of physical law itself. This vision requires us to think on cosmic scales about human purpose and meaning. Instead of seeking happiness and fulfillment within the narrow confines of individual lifetimes, we might consider our role in the vast evolutionary process that connects the Big Bang to whatever cosmic future awaits. Our scientific investigations, our artistic creations, our moral developments, and our spiritual insights might all contribute to the universe's ongoing evolution toward greater complexity, consciousness, and creativity. Every human achievement, no matter how small, becomes part of the cosmic story of emergence and transformation. At the same time, this perspective demands humility about our ultimate knowledge and control. If the laws of physics themselves can change, then all human understanding becomes provisional and temporary. The scientific theories we've developed, the technologies we've created, and the civilizations we've built all depend on cosmic conditions that are subject to change. This doesn't make human achievements less valuable, but it does place them in a larger context of cosmic becoming. We are participants in a drama so vast and long-lasting that individual human lives represent only brief moments in its unfolding. Yet each of these moments contributes something unique and irreplaceable to the larger story. The challenge for humanity is learning to live meaningfully within this cosmic perspective. How do we maintain hope and motivation when confronted with the ultimate impermanence of everything we consider real? How do we find purpose in a universe where even the fundamental categories of existence might be temporary? The answer might lie in embracing the creative process itself, rather than seeking permanent products or final destinations. If the universe is fundamentally creative, then participating in that creativity, contributing to its ongoing evolution, and adding our own unique voice to its vast symphony might be the deepest form of meaning available to conscious beings. This means valuing, becoming over being, process over product, journey over destination. Instead of trying to build permanent monuments to human achievement, we might focus on contributing to the ongoing flow of cosmic creativity that will continue long after our current form of existence has been transformed beyond recognition. The possibility that physical laws have an expiration date also calls for new forms of wisdom and maturity as a species. The petty conflicts and narrow concerns that dominate much of human affairs seem absurdly small when viewed from the perspective of cosmic evolution. If reality itself is at stake in the long-term evolution of physical law, then human survival and flourishing require unprecedented levels of cooperation and long-term thinking. We might need to evolve beyond tribal identities and national boundaries toward a truly planetary and eventually cosmic perspective. The challenges and opportunities presented by temporary physical laws affect all of humanity equally, regardless of race, religion, nationality, or ideology. This shared cosmic destiny might provide the foundation for new forms of human unity and purpose. Instead of competing over limited resources or conflicting beliefs, we might collaborate in the grand project of understanding and potentially influencing the evolution of physical law itself. But even if such collaboration proves impossible, even if humanity ultimately fails to mature as a species, the cosmic story will continue. The universe has been creating and recreating itself for nearly 14 billion years, and it will continue to do so long after human civilization has passed into history. In this vast context, every moment of human consciousness, every instance of love and creativity, every glimpse of beauty and truth becomes infinitely precious precisely because it is temporary. The laws of physics that make these experiences possible represent a brief flowering of cosmic creativity that will eventually give way to other forms of beauty and meaning that we cannot yet imagine. If physics itself has an expiration date, then everything we understand about reality, from atoms to galaxies to life itself, exists within a fragile window of cosmic stability. Outside that window, in the vast spaces of possibility that cosmic evolution might explore, reality might be unrecognizable by current standards. This vision is simultaneously terrifying and wonderful, humbling and inspiring. It reveals existence to be far more precarious and far more creative than we ever imagined. We find ourselves not in a finished universe governed by eternal laws, but in a cosmos still in the process of creating itself, where we have the extraordinary privilege of being conscious witnesses to and participants in its ongoing transformation. Whether the laws of physics will actually change during any human-relevant timescale remains an open question, but the very possibility forces us to appreciate the remarkable improbability and preciousness of our current cosmic moment. In a universe where even physical laws can expire, the emergence of conscious beings capable of contemplating their own existence represents an achievement of staggering significance. We are the universe becoming conscious of itself, if only temporarily. We are cosmic creativity expressing itself through human minds and hearts. We are temporary arrangements of matter and energy that have somehow gained the ability to wonder about their own nature and purpose. If that's not miraculous enough to inspire awe and gratitude, regardless of how long it lasts, then perhaps we haven't yet grasped the true magnitude of the cosmic gift we've been given. In a universe with an expiration date on its very laws, every moment of consciousness is a triumph. Every act of love is a victory, and every glimpse of truth is a celebration of the extraordinary creativity that brought us into being and sustains us still.